Let us pray. Let us pray. Heavenly Father, first of all, we want to thank you for waking us up this morning. God, we want to thank you for your many mercies. We thank you for watching over every single one of us that are currently on this meet and who will be on this meet. We ask that during this session, the information resonates in our mind, that we remember everything that we've been taught, we will be taught, and help us to store it in our memory and to use it accordingly. And we ask that you just help the teacher, help her to effectively um, teach the information and help us to understand what we need to understand, and help her to give us ease our minds. I mean, ease our minds and help us to feel less anxious if some of us are feeling so. And we ask that you just help each one of us to just stay calm, be focused, and do what we need to do, and continue to be with us and guide us. In Jesus' name we pray. Amen.
Amen. Thank you very much, Daniel. All right, Mr. Borrell will have to make sure that he gets you to feel less anxious.
No,
All right.
not me. No, into her. So,
No, he thought it
so
was me, but it's you.
no, Daniel. You know how you gonna know? You understand? Cause you never pray for me at all, no, Daniel. All right. All right.
Okay, so students, we have with us today our master teacher, Mr. Burrell. He did a first session with us some weeks ago, and he's here to finish up on organic chemistry. He presently teaches the advanced chemistry course at St. Andrew High for girls,
Yeah.
and he is surely qualified to bring you through this final segment. So over to you, Mr. Burrell.
All right. Thank you very much, Doc. Good afternoon, everyone. Welcome to Chem Camp's Organic Chemistry Part 2. All right. So in Part 1, you guys heard about my dilemma, where I was wondering what's going to happen with basketball. You know, my side is now out of the competition. Luckily, we had some time off. So I had like 2 weeks before now to recover from that loss. So I am now okay and happy to be here with you. All right, I hope everyone is ready and rearing to go. We're going to be looking at some past paper questions. And I was asking, I was thinking of 5 years worth. Would you prefer to start from 2015 up or 2019 down? Let me give you that choice. What say you? 2019 down or 2015 up?
All right, type in the chat. Okay, there's some person that's saying 15 up.
Up. All right. All right. 2015 up it will be then. Let me start sharing my screen. And let me disable some stuff here. All right, not seeing the one I want to disable. All right. So it's a 2015 up. So let's start with this one. So we're going to run through as quickly as possible. You'll notice that some of the other questions will be familiar to you, and we'll discuss them as we go on. Once I start teaching, I'm going to close my video, okay? And then I'll come back on later on. All right, let me do that now. So the first question we're looking at is 2015, and this is number 3. So it is number 3, and then we go number 5, then we go to 16, and so on. So in the first instance, go ahead and have a look at the question first. 3A, the fully displayed structures for 2 hydrocarbons, compound A and compound B, are shown below. Have a look at compound A, have a look at compound B. Name the homologous series to which compounds A and B belong. All right, so you can go ahead and type your answers in the chat and we'll discuss. If you are anybody having any difficulty, stop me so we can stop and go over and discuss the issue.
Okay, so the answers look like A alkane, B alkene.
All right. Hold on. I'm looking for my writing tool. I'm not sure if. Let me check right here, sir. Suka is not
Should be
my.
there at the top.
Yeah,
It's not
looking for
there.
it. I'm not seeing it. It should be a pen-like structure.
You mean on the PDF or on the screen?
No man, on the Zoom.
Yeah, I think you have to go click at the top or something. View.
Yeah, man. I'm looking for it right there. I see optimize
I don't
sound.
know.
That I'm not seeing it. I'm not seeing the pen.
I'm not sure why.
Not seeing the pen at all. Where are you, pen?
Isn't it always there?
Yes, it was there the last time. I used it the last time. Ah, wow.
Maybe if you change the the full screen, I don't know.
Excuse me, sir. Did you press annotate?
I'm not seeing it. That's what I'm looking for. Not seeing annotate. It was there the last time. It's not there now. Record the cloud, meeting info. I'm at the three dots. All right. Remote control, pause, new share. It's not there at all. Hold on. Let me stop sharing for a second. It's not there at all. Where is it?
Somebody says annotation has been disabled. Oh, I don't know if
So you have to enable it from your end.
All right, let me check it.
Yes, please. Because it's always at the top.
Oh, so where you go to do that? But
Probably
you're
have to go
co-host, you're co-host.
into settings. Yeah, but these things are normally done from the web portal.
Oh.
I'm not seeing it from my end at all. Let me go into security. Hold on, let me see. Share screen, enable waiting room lock. No, I'm not seeing annotate. After this, probably I come to my whiteboard and I probably work. See, when I open the whiteboard, it's there.
So I don't know
yes, it's there. All right, let me stop again. Let me come out and see if it's still there. See, it's not there. All right, so what I'll do is we'll just talk and I'll go to the whiteboard and write and draw stuff if needs be. All right, so what's your answer for the first part? Name the homologous series to which compounds A and B belong. What is compound A? Have a look at it and tell me the homologous series, the family of compounds from the last time we discussed this. What are your answers?
So they had given A for alkane and B for alkene.
A for alkane and B for alkene. How can you be sure that you are correct? How can you be sure?
The carbon double bond.
All right. You look at whether they have single bonds or carbon-carbon double bonds. And you can always use the general formula, CnH2n plus 2 and CnH2n. All right? Because if you have 4 carbons, 1, 2, 3, 4, when you put the number of carbons in the formula, you should get the number of carbons here and the number of H's. So you are all correct. All right. Thank you very much for that. State the name of each compound. Who can name compound A and then compound B?
Somebody said butane.
For which one? The compound A?
Well, somebody's giving a
butane.
Right. 2-methyl butane.
2-methyl butane. Yes, that's correct. All right, before I continue with B, listen carefully. Remember now, in writing the name for this is a branch and it's on the second carbon, okay? You always start the numbering from the lower end. So this is 1, this is 2. You would not say 1, 2, 3, and then say 3 methyl. Is that clear, everyone? Are we clear there?
Yes, sir.
All right, so it's 2, but you must say 2 dash, the hyphen. So it's 2 hyphen. Whenever you have a number and a letter, a hyphen must be there. So 2-methyl butane. That's correct for the name of compound A. What about compound B?
Butene. Butene.
Butene. Okay, that's correct. That's correct. But I prefer butene.
Butene. Yes, sir.
Butene.
Butene or
Yes.
2-butene.
Or 2-butene. Even though the preferred way is the butene. Now, if you notice here, I'm so sorry I can't write. If you notice here, this is 1, this is 2, this is 3, this is 4. So we have the carbon-carbon double bond. The double bond is between the second carbon and the third carbon. But we in the rules, the nomenclature, the IUPAC system, you go with the lower number in the name. So it's 2. Sorry, so it's the carbon double bond is between the second and third carbon. So we say but because it's 1, 2, 3, 4, and but is the prefix for 4. So but-2-ene. And you're saying that the double bond is between the second and third carbon, but we go with the lower number. Any questions? Any questions there so far?
No questions, no questions.
All right, good. Moving on now to defining structural isomerism. Now, again, class, the last time I told you that you could define isomers. And so you don't get confused. You simply say isomers are, okay? If they say define isomerism, it is the existence of, okay? So who want to try and tell me what the definition is for structural isomerism?
Okay, just a minute, there's a raised hand.
Okay.
Go ahead. Go ahead. Who is speaking?
This is Daniel.
Okay, just a sec. Let me just, yes, go ahead, Daniel.
Okay, structural isomerism, can it be when a compound can be arranged, the molecules in a compound can be arranged in different forms?
All right, yes. Yes, in a nutshell, you are correct. All right, but you simply say the existence of 2 or more organic compounds with the same molecular formula. You must say that, okay? Mute that mic for me, please. Yes, the same molecular formula, but different structural formula. In other words, the arrangement of the carbon atoms are different, okay? Okay, but not only the carbon atoms, you can have a different arrangement of where the double bond is. The position of the double bond can also be different. So it is the existence of 2 or more. Okay, so we're looking at the definition again. So we're saying that it is the existence of 2 or more organic compounds with the same molecular formula but different structural formula. You must say that in your definition. Good? Good?
Yes, sir.
All right. Here why you must say that. When you write, all right, let's look at this example first. Draw the fully displayed structure of one structural isomer for each of compounds A and B. All right, so let me go back to A and B. So I'm going to draw a structure that's an isomer of A and then one that's an isomer of B. I'm going to go to my whiteboard and then you'll see something. Let me share the whiteboard now. All right. So we had one. Oh, let me change this. We had 1, 2, 3, 4, and we had a branch there. But a branch there. And the other one was 1, 2, 3, 4, and the carbon-carbon double bond was there. In the interest of time, I'm going to leave off the H's, but you must put them on in the exam. All right. Who can tell me what to do to form an isomer of this particular structure? What do I do? So this was 2-methyl butane. Anyone? What do I do with this structure to write an isomer? So
Sir, you can move the methyl group.
Move the branch group, the methyl group to where?
Yes, sir. You can put it on the third one.
Put it here, sir?
No, it would be the same thing.
All right. If you put it here, it's going to be the same thing because you always start numbering from the side closest to the end. You see it? So if you put it here, then this becomes...
Sir, my bad.
No, man, nothing
Sir,
wrong.
you can change it. Sir, you can take off the fourth carbon and put it on the second one so you could get 2,2-dimethyl butane.
All right, so good. I like that one. So you could have 1, 2, 3, and then remove this one and put it here. And this was there already. That's one. So now you have 2,2 dimethyl. That not butane though. The parent now would be prop. So it'd be 2,2 dimethyl propane. Good. What else could I do? What else could I do? Let me just put
Sir,
on
could
some
you move
H.
the methyl group to either one of the end carbons?
Yes. Good one. That's a simpler one. Yes. So move the methyl group to one of the ends. So I could go 1, 2, 3, 4, and then 5. All right, let me erase this one. What's the name of this compound? This one here.
Pentane.
Pentane.
Yep, pentane. So 2,2 dimethyl propane. So look now, people. 2, 2. Number and number, comma. 2,2 dimethyl. Then what?
Dash.
Di, which means 2 of them. So I have 2 methyl groups, so dimethyl. And 1, 2, 3 parent. So propane. Yes. Thank you. And this is pentane. Do you remember the definition of an isomer or isomerism? Same molecular formula. So if I should say CnH2n plus 2, right? But different structures, all of these structures should match this particular formula. Are we clear there?
Yes, sir.
So if I say C5, it's H, 2 times 5 is 10, plus 2
12.
is C5H12. If you count off everybody, you get C5H12. Good? All right. I'm going to move to the next one now, which is the but2ene. 1, 2, 3, 4. 1, 2, 3, 4. All right. Go ahead now and give me an isomer of but2ene. Anyone?
But1ene.
But1ene. All right. So you're saying move the double bond from between the second and third carbon and put it between the first and second carbon. Yes. Anyone? Look here. Make sure that this should not be a bond here. Make sure around each carbon you have 4 bonds. So let me put in the correct bonds. So we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1 must come here. Okay? So don't forget that, class. So check the number of bonds around each carbon. Remember, carbon is tetravalent. So you must have 4 bonds around it at all times. All right. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1 more there and that. How we stay? Can you find another isomer? Anyone? Can you find another isomer?
Sir, 2
Mhm.
2
2. Once you say 2, give me the branch first. So the 2 is saying you want to put a branch on the second carbon. So what's the name of your branch? So 2.
methyl.
Thank you very much. 2 methyl. Methyl is fine. I prefer methyl though. That's what you can say methyl. That's okay. So 2 methyl. Let me use what you use. 2 methyl. What?
But2ene.
Not but. Because but sound too funny, miss. Say but. But is very funny. All right. No, but if you let's say you remove this group here, so and put it on the second carbon, then you have 3 carbons in your parent chain. So it's not gonna be but. It's gonna be
Pro.
Pro. Yes. Yeah. Yes. So let's put the methyl group there. Make sure you have 4 bonds around each carbon. And now that's that. So 1, 2, 3, 4. Good. So now this is 2 methyl prop. Now look here. You could say prop1ene, but propene is okay because it's only 3 carbons. So you can only have it here or here, and it's still the same name. Tell me if I'm making sense there.
Yes, sir.
In
Yes,
other
sir.
words, we have that, or you could have this. Same thing. So instead of saying prop1ene, you just say propene. So there's no need to state the number for this case because on either ends it's the same thing. So propene. All right, how we stay with that so far? Oh, good?
Yes, sir.
All right. Now look here. It's an alkene, so it is unsaturated. So we go CnH2n. So it's how many carbons? 1, 2, 3, 4. So it's 1 C4 H8. If you count each of them, and this is how you can know if you're correcting on people, you should have the same formula, but different structures. So you should have 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8. And if you check any of them, the same thing should happen. Are we clear? Any questions so far?
No, sir.
All right. Can you find one more?
Sir.
Go ahead.
I'm having a when you come to the alkenes with defining the isomers, I don't quite sure how to count the branches when you have the double bonds. What's the easier way?
All right. So look now. Thank you for your question. Look here now. Let's say you're single bonds. So you have 1, 2, 3, 4. Let's call it methane. 4 bonds. Let's do another alkane, but you are now 2 carbons. So it's 1, 2, 3, 4, 5, 6, 7. So each carbon has one single bond. Well, single bonds around it. Now, if you have an alkene, you're now unsaturated. This is a double bond. You see it? So it's 1. Use a different color. So it's 1, and that's 2. You see that?
Yes.
And then now 3, 4. Okay. So 3, 4, and then the same thing for the others. You go 1, 2, 3, 4. Okay. So you can never have this. If you have more than 4 bonds around it, it is incorrect. You see that? So you have 1, 2, 3, 4, 5. You can't have 5 bonds around carbon. Must be only 4 bonds. Remember, carbon is tetravalent. Are we good so far?
Yes, sir.
All right. Any other question before I move on? I'll go back to the question. Any others? Oh, I was asking. Give me one more. No, all right, give me one more isomer. One more isomer of this. Give me one more isomer. Anyone? Anyone?
Nothing there.
Nothing there. All right, let me tell you. And don't forget it. Yes, somebody.
Daniel wants to answer. Go ahead, Daniel.
Go ahead, Daniel.
You can put a methyl branch.
No more methyl branches, because if you put a methyl branch, you'll go back to the same but-1-ene, right? You put a branch already, you know, which I showed you earlier. So, but you can't put any more branches because you count from where the double bond is. So it's always 1, 2, 3, 4. So the one with the branch earlier was like this. Branch was there and that was there. So you go 1, 2, 3. That's the branch. Okay. So you can't do anything else. If you put this here, it's the same thing as this one. Have you heard about cyclocompounds? The rain is falling heavy. Look at here. Cyclo. All right. Cyclo are ringed compounds. So let me show you what a ring compound is. So if I say 1, 2, 3, this is a ring compound.
It takes off one of the hydrogen though.
Yeah, man. That's why I'm gonna go with a cyclo for the other isomer. So this is not the isomer. I'm not showing. This is a 3-carbon compound. That's a ring compound. So you could see it like this. So this is cyclopropane. You see that? So the cyclo is suggesting it's a ring. So cyclopropane. Always stay so far. That makes sense?
Yes, sir.
So this then would be cyclobutane. And how many carbons do I have in this?
4.
4. How many H's?
8.
Did it match what the others had over here in terms of number of carbons and H's? So yes, so this is another isomer. Cyclobutane is another isomer of but-2-ene, but-1-ene, or 2-methyl propene. Are we clear so far? Because they all match, they all have the same molecular formula. Are we good so far?
Yes,
Yes.
sir.
All right.
Sir, could you go to the cyclobutane?
Second,
Sir, could you go back to the cyclobutane,
sure.
please?
So another way you could do it, you just see the box like this, where each of the corners represents a carbon.
Okay, sir. Thank you.
All right. Yep, no problem. All right. Let's go back to the question. All right. What we say so far? Everybody all right? Was this the question? Yes.
No, further down.
Yes, that's
Yeah, man.
That's
Is
it.
it?
Just go down to the isomerism. Yeah.
Yes. All right. So we just did this part here. If my pen was up, I'd put the things here, but we can do more stuff there. All right. Now we're looking at polymer, and polymer is at the end of organic chemistry. The rain is falling really heavy here. It's at the end. So polyethylene is manufactured in Trinidad and is used extensively throughout the Caribbean. Define the term polymer. Poly. Anybody can define polymer?
Sir, polymers are substances made through the combination of smaller, simpler subunits called monomers.
Yes. All right. So you are correct. And what I like with your answer, people, listen, if you give that answer and I give my answer, all I'm going to look for are certain words that must be in it. So don't go and swat and come back and give the exact answer. Just give it the way you understand it, but ensure you have the correct words. Some words must be in it. For example, you must talk about monomers. Okay? You can't define polymer without using the word monomer. All right? So polymers are your macromolecules, your large molecules that are made from joining smaller units called monomers. Now,
Sir,
yes.
it is made up of the same repeating monomer.
Yeah, man. That's fine. That's why I said small repeating units. So that's fine as well. Now, you must say monomers make up your macromolecule, your large molecule. And normally, a macromolecule is 50 units or more. Okay? So polymers are your macromolecules that are built up from small or smaller units called monomers. And you could add that normally it's to be defined as a macromolecule, you're normally 50 units or more. What does that sound?
So
What does that sound, class?
So can you repeat back the definition?
Sure. So we say define polymers. So polymers are large molecules. You could put macromolecules instead of large molecules. So there are macromolecules or large molecules that are built up from a number of smaller molecules or units. Smaller molecules or units called monomers. So let me show you something. It's a polyethylene, right? Polyethylene. So what poly mean? Anybody can tell me what poly mean?
Many.
Many. Thank you very much. So many ethene. So what's ethene? 1, 2. Now look at this, class. Let me show you something. If you see ethene like this, let me put it like this, and you are joining them, this won't work, okay? Because you're going to put one with another. So what do? Move this out of the way and put it down here. So move this bond out of the way and put it right there. So to draw your units, you go like this. That's one ethene. Let's do another one. Normally, it's about 3. They ask for 3 repeating units. Normally, so that's the next one. And another. So what's going to happen is this. This part will open up, the bond here, and this end will open up so that they can join. So you'll have it looking like this. Single bond, and that part's open up there, that opens up there, and you have your H's there. This part will now join to this carbon. So the sides open up. And that's why you're basically adding them together. Is that making sense?
Yes, sir.
All right, so you're adding them together. Now, because it's a macromolecule, it's a large molecule, what we do is I put some dots to show that this is a partial structure. So it's not the complete structure. So the broken lines is suggesting that it's a partial structure. Then I must do something and put a bracket here and put N, because this is our repeating unit that is going to continue on and on and on for 50 units or more. Tell me if you're with me so far.
Yes, sir.
All right, so this is your monomer. So your monomer is ethene. So ethene is the monomer. And the polymer, notice many ethene now becomes polyethene. Polyethene. Tell me if you're okay with that.
Yes, sir.
All right.
Yes, sir.
No. So units, large molecule. Now, what's the difference between the small unit and the large unit? What do you see? Look closely.
Sir,
So
the
there's no
presence
double
of
bond.
no double bond is in the second.
All right. Good. So you know that CSEC could ask you to define, to show how you would distinguish between the two, between the monomer and the polymer. And what do we use to differentiate between an unsaturated substance and one that is saturated?
The double bond.
No, man. What reagent? What reagent? If you're testing
Sir,
for it in the lab.
you can use bromine vapor
water.
or bromine water.
All right. We soon talk about bromine water because I want to make something clear to you. But we soon talk about bromine water. So bromine vapor, bromine water, yes, or bromine liquid. When I reach a bromine, to distinguish between the two, I'm going to show you that even though at this level they allow it, at the 6th form level, if you say bromine water, you can't add BR across the carbon-carbon double bond. Because bromine water, you will form a bromo alcohol. But I'll get to that. Don't worry about that right now. At this level, it's okay. Aqueous bromine, BR. Okay? I just want to make that clear. So when it comes to 6th form, you don't get confused. All right. So good. So you can distinguish now using the test for unsaturation. And somebody mentioned potassium manganate 7 earlier.
It's a permanganate.
Yes. Yeah, man. Same thing. Potassium manganate 7 or permanganate. All right. You could use that as well. What would be the color change for using the aqueous bromine or the bromine liquid? What would be your color change?
It would rapidly decolorize the bromine.
All right. So the bromine will become decolorized. And bromine is what color?
Brown or red
Brown.
brown.
Red brown, reddish brown.
Red brown.
All right, reddish brown. Again, I don't think that'll kill you if you say brown. Okay, you'll get a mark still. So that's correct. What if you're using now the potassium permanganate? What would be your color change?
Purple to colorless.
Purple to colorless.
Purple to colorless. All right. Again, at this level, colorless is fine. At the 6th form level, pale pink is what we would accept. But that's fine. All right, pale pink. But that's okay. Good job. All right, let's go back then. Everyone understanding so far?
Yes, sir.
All right. Somebody was trying to do a little extension, to make sure you're okay. Let me go back to yes, over here. All right. So we're okay with defining polymer. What is the type of polymerization used to manufacture polyethylene?
Additional
Addition.
All right. Addition. Don't say additional. Addition. Okay. Addition. I'm saying I'm stressing that because I know sometimes you say oxidization. That's the next thing you must be careful of. Okay, it's not oxidization, it's oxidation. So with chemistry, you have to be very careful with the language. Are we clear so far? Yes.
Yes, sir.
All right. So we're good. So
Addition, sir.
why is it addition? Let's go back to the whiteboard. Good question. All right. Look at this. Notice, when you are unsaturated, a reaction of alkenes is called addition. So let me show you something. If I have 1, 2, 3, and let's put a double bond there, and these are H's, and let's call this X and Y. If I'm adding X and Y to this, I'm going to add it across the carbon-carbon double bond, because it is unsaturated, so it can hold more things. Do you agree with that?
Yes, sir.
Yes, sir.
Think of a sponge and water on the floor, and you put the sponge over the water, and it sucks up all the water, and there's no more. But think of the sponge now being saturated, and you try to take up the water, it will run back out of the sponge. So the alkene here is unsaturated, so it will now accept 1, 2, 3. This will open up here, and it will accept the X and the Y. Do you agree with that?
Yes, sir.
Yes,
So
sir.
it's the same thing would happen if it was Br2, bromine, or HCl, H and Cl, or water, H and OH, etc. With what we did a while ago with the macromolecule, the monomer forming the macromolecule, we can add it across the double bond. So let's use the same thing. This is propionine, right? Or propene. So let's say I'm going to add this. 1, 2, 3. I can't add it like this, so I have to change something. This I must move out of the way. Another H must be here. So I must move this out of the way. So let's put it above. So let's put CH3 above. Now I have C. This is up here, C, double bond, C. And that's another H. So that's H here. So that's H. And that's a H. And that's a H. Let's put that H down the other side too. Put it down here. H here. How that look? Now you can add across here and here to add another molecule of propene. You see that, class?
Yes, sir.
So it's addition because the compound, the molecule we're looking at is unsaturated, so you can add things to it. It can take more things on it. Okay? If it is saturated, then you can add. What would you have to do if it is saturated?
Substitute.
Substitute. So think of you are on a table now. So this is a table. And you are here. This is a chair. Chair. And all the chairs are occupied. And if somebody come now to go on the chair, let's put X on a chair. Whoever is on a chair must get up. Let's put Y. Must get up and move so X can come on the chair. So this is called substitution. Are we clear so far?
Yes, sir.
Yes, sir.
Did I answer your question as to why addition?
Yes, sir.
All right. So let's go back. Any other questions in the meantime, in between time?
Sir, could you use a dehydrogenation reaction to form it to be unsaturated? I mean,
Yes. You're talking about adding H2
yes,
or
sir.
removing H2.
Or
Yes.
removing.
Yes.
I think,
But at this level, we mainly do
right.
adding H2. We don't remove H2 at this level.
Right.
Okay.
All right, sir.
All right. But that's good that you can think about that. All right. Good thinking. Moving on. So we said define polymers. We're okay with that. Identify the type of polymerization that is used in the manufacture of polythene or polyethene. Notice I said polythene a while ago. So you could even say polythene in the exam. It's the same thing as polyethene. Are we good?
Yes, sir.
All right. Now give me some uses now. Why my
Used to
dog make up here
manufacture
then?
PVC. Used to manufacture plastics.
All right. Don't you say PVC? You say PVC, right?
Yes, sir.
All right. So PVC is coming from vinyl chloride.
Polyvinyl chloride.
It's coming from vinyl chloride, right? Or what? Chloroethene. Let me show you that. Let me show you that one. With one, you have a chloro on it. Yes. Well, you can't say chloro because it's only two of them.
We use high pressure and heat to form the polyvinyl chloride.
Right. But we're not going into that part yet, right?
Okay, sir. Not hearing you. Mr. Burrell?
Yes.
Can you repeat the question?
No, man, the question was, let me go back to the question. The question was, state 2 uses of polyethylene, but somebody mentioned something about polyvinyl PVC, polyvinyl chloride. So I was just trying to show you that we are not dealing with polyvinyl chloride, because this is how it looks. We're looking at ethene that forms polyethylene. True? So what I want is the uses for polyethylene.
Plastics.
Yes. So the manufacture of plastics. All right. Now you have 2 types of plastics, you know. Okay. You have like your single-use plastic bags, and you have your crates. So same for both. Okay. One is called low density, and one is called high density. That's correct. So plastic bags is quite fine. So the manufacture of plastic bags. Give me another example.
Sir, for agriculture.
I didn't hear you. Go ahead.
Sir, I think agriculture.
The rain and the thunder is so loud. All right. You said agriculture. Remember a while ago, I spoke about two types of polyethylene, low density and high density. So the high density one would be your food containers, your crates, your bottles, and so on. Okay? So the first one is the manufacture of plastic bags, which would be your low density polyethylene. And the other use is your high density polyethylene, like your food containers, your crates, your bottles, and so on. Those thick, heavy plastics. Good? How we say?
Yes, we're good.
All right, good. Go back here now. So we reach now, state now the name of one other polymer. This is now when you say what?
Polyester.
All right.
PVC, sir.
All right. Hold on there. You said someone said polyester. Let me stop you right away. What is this question dealing with?
Polyethylene.
Which is an addition polymer. I'm sorry if I sound like I'm shouting. It's because the rain is so loud, so heavy, so I'm hardly hearing.
We're hearing.
Let me apologize if it sounds like I'm shouting. Yes, class. We're dealing with addition polymers. Clear? Clear, class?
Yes, sir. Yes, sir.
Somebody said polyester a while ago, right? Polyester is a condensation polymer. So CXE, they want examples of addition polymer.
Polypropylene, sir.
Propene.
Propylene.
Yes, poly. You just give me PVC. Remember PVC?
Yes,
this as well. PVC. Put on my H's here.
Sir,
right?
PTFE, polytetrafluoric ethene.
That is correct. Which is what? This one like this with all your F around. 4F. Tetra.
Yes. Sir,
what about polystyrene?
Yes, somebody mentioned that in the chat.
Oh, in the chat. Okay. All right. So this is what polystyrene looks like. Let me get a new page to show you. So if you see the exam, you don't go crazy. Look, class. If you see this, C6H5. So that the one is gone because the bond must come now to put the carbon-carbon double bond here. And these are H's. Now, look. This is your benzene minus 1H, which becomes a phenyl group. So benzene is C6H6. C6H6. So this is benzene for you. Double, single, double. I have 1H around it. One at each section there. C6H6. All right. So these are carbons. Now, if 1H is gone, this is where the other part will be attached to this carbon here. So you could see it looking like this. C, put your ring. All right. Put your H here. Put your carbon here and the other H like that. So this becomes styrene. Okay, so polystyrene or polystyrene, some might call it polystyrene. So polystyrene is just opening up now this bond here. So you have 1, 2, we're going for 3 units. Put the ends there. Put on your right. Put on your H. Do the same thing now because now it is repeating units, right? So this will be the benzene ring, the phenyl group. A phenyl group right here as well. Right here. And now that's H. H. So these are addition polymers, okay? H, 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 H. And put your square bracket around this one here and put the N. So it continues. So leave the lines. Oh my goodness, my dog. Leave the lines to show that it's a partial structure. So this is the repeat. All of this is your large molecule, your macromolecule, and this is your repeating unit. Now, if you get a large structure like this and they say, what is the monomer? What do you do? Who can tell me? What do you do?
Sir, draw only one of the structures.
All right. Use the repeating unit and put back the double bond. Does that make sense?
Yes, sir.
So just see there, this is this, but the difference is the double bond is here. Same thing. So use this repeating unit, put back the double bond. So from your macro molecule, you can get back your monomer. And your monomers is what form your macromolecule. And these are all addition polymers. Class, hint, all of the monomer is used up in forming the macromolecule. That's why you form only one product. Tell me if that's clear.
Yes, sir.
All right. All of the monomer is used up in forming the macromolecule, so you only form one product. When it's condensation, it's different. All the monomer will not be present in the macromolecule, hence you'll have more than one product. Okay? All right, so we're good so far. So let's go back here. So you gave me several, of course, but no several just in case. So we say, give me them again. You said PVC. We said polystyrene. You said a polytetrafluoroethene.
Fluoroethene. Yes, sir.
Those are all examples of natural, not natural, of addition polymers. And addition polymers are not natural polymers. Let me make sure I say that. So the word they use is synthetic. Synthetic. Malith.
Synthetic,
Clear?
yes.
Synthetic. Malith.
Let me put it in the chat.
Yes. It simply means man-made. Okay? So all addition polymers are man-made. I'm just giving you some extra information in the event you get something else in the exam. Any questions before I move on to the next part of the question? Any questions, class? No?
I think somebody was asking about condensation polymers. I told them that you would treat it in a bit. So
yes.
I have a question on it later on.
Yes, I'm trying to answer the question, so I'll discuss things with regards to what we're doing with the question.
Right.
Yes. So if I meet upon one, I will deal with it.
Right.
All right. We're at now number 5 of 2015. Now, people, look at this and tell me where have you seen this before?
Sir, the manufacture of sugar.
Yes, and what section of the syllabus is that?
The first part with the separation technique.
Thank you very much. So you can get this anytime. All right, have a look at it. Read it first. I'll give you a couple of seconds to read it and look at the diagram. Let me read first, then I'll scroll to the diagram. And then I'll ask the questions.
Probably if you make it a bit smaller so they can see more of the question.
Yes, hold on. So look at the structure first, and then I'll scroll to the questions after, okay? All right, are we ready? So this is the industrial processing of sugarcane. So despite its organic chemistry, remember that alcohols, ethanol is a part of organic chemistry. So they could link it with any part of the syllabus that you are going to do. All right. All right, so you must understand these steps in the extraction of sugar. Well, what is called, before you can get sugarcane, what must you do first? It's planted, you grow it, what else? What's your first step in the process, the industrial process?
Slash and burn, sir.
Slash and, all right, no man, after all of that. After slash and burn. They have to cut it first?
Somebody said crush. Somebody said crush.
You cut. You have to cut it first, and then you crush. Yeah, man, harvest. You cut, then you crush. All right? And then now, after that, now you have something at P. Who can tell me what's going on at P?
Isn't that where you add the lime?
You add the
clarification, sir.
Yes, clarification. Thank you very much. That is where you add the lime. So good. So you're coming together to give me the answers. Good. So clarification, the process involves the addition of lime, which is calcium hydroxide. Okay. What is the purpose of adding the lime?
So to neutralize the acidity or
to neutralize the acid. Thank you very much. And what else? One more thing.
Causes the impurities to precipitate.
Yes. So to neutralize the acid and to precipitate out any impurities. That is at P, and that is called clarification. Are we okay with that so far?
How do you spell clarification?
That's no, I'm saying that's clarification. That's a process of clarification where you add the lime.
Well, Maxim, how do you spell the word?
Oh, spell the word. CLARIFICATION. Clarification.
Thank you, sir.
You're welcome. Thank you, miss. But if you say clarifying now, you have to put the Y in there. Y-I-N-G. All right. So clarification. Now, a part of the process is you produce impurities. That is why you have filtration after that. Do you see that?
Yes, sir.
All right. So that's why you have filtration here. Now, what happens after filtration?
Sir, distillation.
Distillation?
Sir, is it caramelization? Well,
yeah, to a sense, crystallization is the correct word.
Crystallization.
Yeah, man. Crystallization is what will take place here. All right, where you crystallize your salts and so on. So now you'll have now solid with some liquids, and then now you must carry out centrifugation to separate now that. Okay? Are we clear so far?
Yes, sir.
All right, look at this part now, class. So after crystallization, centrifugation, you have your sugars and your product. What will be your product?
Molasses.
Molasses.
All right.
Yeah.
With sugar. Or with
sugar. Yep, you could say that. Yes. No problem. Yes. Good. All right. Now go, come over this side. Why my dog loud? Come over this side. Bagasse. What do you think is going on here at Bagasse? Energy. So it's like the trash. Okay? So this here at part product X is your molasses, or you say wet sugar. Okay? And now this now is your bagasse, which is like your trash, the trash used now to generate electricity. Any questions?
Sir, please go over.
Say again?
Want to go it over.
Go over?
Yes.
All right. So we're doing sugar cane. So we're saying the first thing we're going to do is to what? Cut the cane. All right. They put it on the mill train, which is the cut cane going on this thing that conveyor belt that carries it, and it goes through something now that will crush it and spray it with water. So the crushing and the spraying is to get the juice out of the cane. True? True? Tell me if you're okay with that, you know.
Yes, sir.
Once you get your juice now, you must clarify. So the process of clarification will now take place here, where you add your lime, your calcium hydroxide, okay? That's your base. Why do you add the base? You want to neutralize the acid because acid is present, okay? As well as it will precipitate out any impurities. Impurities in the precipitate form is a solute or solid. So you must now filter it off. So that's why I have filtration. Once you filter it off, the next step now is you're going to do what is called crystallization. When you crystallize things, don't you have to apply some heat to remove excess water? I'm asking.
Yes, sir.
Yes. So in process Q, you are pretty much concentrating your solution. Okay, so you're gonna remove excess water. All right, and while removing water, it is cooling, you're gonna form crystals. So this is your crystallization process. Okay, then now we say you centrifuge, and centrifugation is where you are now separating your solute, your sugar solute from the liquid part of it, the wet part of it. Okay, and the wet part we say is molasses. So now we have a separation of sugar and molasses here. How we stay so far? The person that asked me to go over. You with us so far?
Yes, sir.
All right. So now we come over this side now. I would say, remember now, the cut cane that was crushed and the juice came out of it, that now is like the trash. What are we going to do with the trash? We're not going to throw it away. Okay? We're going to use it. It's called bagasse. And we're going to use it now to produce electricity. Clear? So if you understand this process, the questions that follow must be along that line, not true? So look at the question. Identify the process P and Q. See there? P and Q. So it's a clarification taking place here, and this is crystallization. If this is sugar, this must be molasses. Good? Or the wet sugar. All right? Always stay so far. We're good? State the importance of the centrifugation process. I would say this is done to do what? What did I say earlier? Who can tell me?
To separate
Thank you very much. Yes. From the molasses. Good. Which means that at part 3, what is that part 3?
Molasses.
Yep. And then now look at part 4. I'll bring it back up for you. Look at part 4. The bagasse produced is used in the factory during the processing of sugarcane. In which part of the factory is this bagasse used, and what is it used for? So give me the part first. Who can tell me the part? When you have industries, which part deal with this kind of stuff to generate electricity? Anyone?
So in the machinery department.
All right, we have a special room for that.
In the chat, somebody has generator, question sign.
All right, close. It's a boiler room. It's a boiler room.
Boiler.
Yes, the boiler room. The boiler room is where you generate the electricity. All right. Are we okay so far? Can I move on?
Yes.
Okay. Moving on, we reach what? Part B? Yes, part B. All right. Look at part B for me, ladies and gentlemen. Many Caribbean islands are renowned for the quality of rum they produce. Okay? The alcohol content of a typical rum averages between 40 and 55%. All right. During the fermentation process, in the making of rum, yeast feeds on the sucrose in molasses. Note, this is sucrose first, right? In the molasses, converting it into simpler sugars. And what are those simpler sugars, class? Sucrose into what?
Fructose and glucose.
Fructose and glucose. And the molecules are very similar. Clear? All right?
Yes, sir.
Thank you. All right. So now, let's say now, first thing, let's look at this one. Once you're doing fermentation, let me say this first. You will never get 40% or 55% alcohol just by the fermentation process. Are we clear there?
Yes, sir. It have to keep recycled back.
You have to do fractional distillation. You must do distillation to get a higher percentage. But who can tell me why we can't get a higher percentage just by the fermentation process? Anyone?
Sir, because the alcohol starts to kill the yeast or the enzyme.
Yes. Yes. Well, the enzyme is in the yeast. So if you say yeast or enzyme, fine. Because the enzyme is what is. So not kill though. If you do bio, we know we can't kill enzymes, right? So we say denatured. Yes, we say denatured. So again, watch the language here. So we say denatured. So at a percentage of about, some would say 12, some would say 14. So anywhere between 12 and 14%. Once you read that percentage, the yeast or the enzyme become denatured and hence cannot produce anymore Are we clear so far?
Yes, sir. And that's why the alcohol content of beers and wines are typically from 5% to 10%.
Yes. What's your name?
Because it's fermented.
What's your name?
Yeah, man, Baker.
Yeah, man. Baker. All right, Baker. Respect for that, Baker. Yeah, man. Good. So if you want a higher percentage now, you must do your distillation. Okay? And then now, later on when you reach sixth form now, there's something called azeotropes, which will show you that you can never, ever get 100% alcohol. Never. Okay? You will never get 100% alcohol. So when you reach that level, you'll learn that.
Don't frighten them. Don't frighten them.
All right. Sorry about that. I want to encourage them. I want to encourage them to do it at the sixth form level, miss. That's all.
Yes.
Yes, it's nice. It's fun. All right. So now let's do some questions now. Notice class, it says outline. Wait, during the fermentation, outline using balance equations, which is suggesting what? Using balance equations. What is that suggesting?
So we show the reactants and the products.
Yeah, but not only one equation, more than one. You follow? So the one you're familiar with is when the glucose form the alcohol and carbon dioxide along with the energy, not true? But you must know the other one, which is going from sucrose and the name of that enzyme that cause it to form the fructose and glucose. Go ahead.
Sir, them want the hydrolysis part too.
The splitting part, yeah. Yes, you're the bio.
Yes, sir.
Yeah, man. For you mention that term hydrolysis, I know you do bio. So you're using water to split it, right? And remember I said the molecule, the fructose and glucose were similar. Okay,
somebody's given zymase.
Yes, zymase is the enzyme that will break down which one? The sucrose or the glucose?
The glucose.
The glucose, all right. So let's go there now. So let's say two equations. So let's start from sucrose. So sucrose would start from C12H22O11. So when you have some time, you can go on the internet and look up this structure, okay? Look up the structure of sucrose. Plus water. So water will split the molecule, hence hydrolysis. Clear? So this is H2O plus H2O. Now the enzyme we use here is invertase. That's the enzyme. And now you form two structures that are similar. C6H12O6. So we stay so far. So this is your first equation. All right, so this is your sucrose. It will be hydrolyzed, so water will split it, okay? And you get two equal or two same molecules, same structures. So this one is glucose, and the other one is fructose. Are we clear so far?
Yes, sir.
So glucose or fructose, but we normally use glucose. Glucose or fructose is now what we're going to use now to produce the ethanol. So C6H12O6. Now we use the enzyme zymase. And now this will produce your alcohol, C2H5OH, plus carbon dioxide. Two more, thank you. And of course, energy, okay? Now, if you recall, this is your... Yes, go ahead.
So is this the equation for respiration in plants?
Respiration in plants?
Mm-hmm.
By a person, but this is respiration. It's anaerobic.
No,
but it's not.
No,
yeah,
no.
I didn't think so. I wouldn't think that because you produce the alcohol.
Respiration would be the opposite of the photosynthesis thing there.
Yeah.
I mean the anaerobic respiration.
Okay. Yeah, this is the anaerobic. Yes. Anaerobic. So anaerobic is without oxygen. Thank you for that. So now we're gonna close this. So this is the bong. I can't draw no people. Take time with me. So bring it over here. Bring it down. Bring it in a test tube or a boiling tube. And here I'm gonna have my calcium hydroxide. Now here, what do I have here? You have your sugar. What else?
Yeast.
You have your enzyme. Let say yeast. Fine. All right, and you might have some nitrates, some food for the enzyme. Okay, for the yeast. And it is going to now respire anaerobically. Now, will it respire aerobically?
No, sir.
No, sir.
It will. It will. Let me tell you why. When you set up the apparatus, oxygen, O2, will get inside the container. So before you have your anaerobic, it's going to respire aerobically and use up all the oxygen. That is now why you don't have any oxygen inside. Tell me if I'm making sense.
Yes, sir.
No,
So
sir,
Because I
please come
think,
again.
sir, the oxygen go make it turn ethyl ethanoate, I think.
No, man, not yet. Because remember, when I start producing anything yet, you know. All right, let's say now we have our separate apparatus and it's open, and you pour in your sugar, pour in your yeast and the food. Then you must close it. Then you must put the bung, right? Let me see if I can draw the bung like so. Then you must close it with the bung, right? When you close it, how are you going to prevent O2 from getting inside the container? You can't do that unless you have a vacuum to pull out the oxygen.
Can't you create a vacuum first?
Yeah, yeah. But we don't have the apparatus to do that. You follow? So this is the laboratory setup, you know. So I'm saying to you, once you close it, some O2 must be present in the flask. Not true?
Yes, sir.
So I'm saying to you, initially, the O2 that's there, the enzyme will respire aerobically first. And in respiring aerobically, it is not going to produce any alcohol, you know. It is just using up the oxygen first. So once it respires aerobically and use up all the oxygen, now it can respire anaerobically and produce your alcohol and your carbon dioxide. You with me so far?
Yes,
Yes, sir.
Yes, go ahead. Am I?
This a part of organic chemistry, sugarcane clarification.
Alcohol. No. Well, the alcohol part is a part of organic chemistry. This is a part of atomic structure, the first part of the syllabus, section A. The sugarcane part. But alcohol and fermentation is a part of organic chemistry.
Right. I was saying the fermentation is a part of the organic chemistry
Yes.
part. So you would have to revisit this this aspect of it.
Yes. All right. Any other questions? All right.
Sir,
Yes.
could you explain how you got the glucose from the sucrose? Can I ask me from there?
All right. So we call it hydrolysis. So if you look at the structure, it looks I can't draw it properly enough, people. But anyways, bear with me. It looks something like so. Something like so. Doctor, if me correct in my structure. All right. So this will be split. The water will split the structure, and you have two equal parts. That's why you get 2C6H12O6. Okay. So at this level, all you need to know, and when you go to sixth form and doing bio, you'll go into this in greater detail. I'm not a bio person. All right.
Sir, that structure is incorrect.
No, that's what I'm saying. I'm just showing you two simple things. That's why I get two equal things. Remember, I'm not saying that this is sucrose, you know. All right. I'm just illustrating that why I get two equal structures here. Got it? So my structure is not correct. I'm just illustrating that why I get two equal parts. So 2C6H12O6. So instead of saying 2C6H12O6, I could say C6H12O6 plus C6H12O6. Make sense?
Yes, sir.
All right. So let me say that. Let me rub it out. This is not the correct structure of sucrose. All right. The bio process can tell me the correct structure, or you can go and look it up. All right. So the water will split it, hence hydrolysis. You get two equal structures. And now we use the glucose along with the enzyme to respire anaerobically to produce your alcohol and your carbon dioxide. How do you know when you're producing alcohol? Who can tell me?
Sir, from what I remember,
Mm-hmm.
wait, sir, is it that with the thermometer? Like when it gets...
No, that's a fractional distillation.
Sir, the alcohol will float on top of the water.
You can see the alcohol float on top of the water, miss?
No, they're immiscible liquid. They're immiscible liquid, sir.
All right. Yeah, it's immiscible, but that's not what I'm looking for. Go on again. One more time.
They're miscible, just to clarify here.
Yes, alcohol and water is miscible. Yes,
Miscible, not immiscible.
because it have the same hydrogen bonds. But that's not it. Look again. Look at the structure. Look at the diagram. Sorry.
Sir, so will you see like I want to say bubbles emerging from the
Effervescence, bubbles, yes.
effervescence
And
and
the lime water
and
turning
water
cloudy.
form.
Because that is saying that you are producing carbon dioxide. And from you produce carbon dioxide, you also produce
Alcohol.
yes. In other words, carbon dioxide is like a byproduct of producing alcohol. In this case, clear? So we use the carbon dioxide to say that we are producing that. All right. Now, we produce the alcohol, right? Let's say we open it now. We open the container, and after a while, it smells sour. What happened to it?
Sir, it has fermented.
No, man, we ferment it already now. We form the alcohol. But you leave it, you open it and you leave it open.
Okay,
And it smells sour.
There's an answer in the chat. Somebody says turn in vinegar.
You turn acid. Yes. All
Yeah,
right, yes.
acid.
Yes, so the ethanol will be converted to ethanoic acid. Now that process is called oxidation. And the reason for that is oxygen, O2, is that oxidation, is that that substance that will oxidize the alcohol to ethanoic acid. Are we clear?
Yes, sir.
So it's an oxidizing agent, is the word I was looking for. O2 is an oxidizing agent in this case. Are we clear so far?
Yes, sir.
All right. So did you know the two equations? Most
I
times.
did know the first one.
You didn't know.
I know the Siamese one.
Yeah, I know, because I don't think this one is in the syllabus, but most times they ask for this one alone. But as you can see, in 2015, they asked for equations. So you have to come from sucrose to glucose and fructose, then glucose to the ethanol and carbon dioxide. I know you know invertase and zymase. The bio persons, however, would be familiar with this one. So that's why whenever you're teaching this topic, you must have integration between topics or subjects. Clear? All right. How is it? Doc, everybody all right?
Good. Yes, yes, sir. Yes, sir.
And you okay?
Sir.
Yes.
Sir,
yes.
So Miss just typed in the chat that the alcohol one is oxidized to
well, I'm just
ethanoic
explaining
acid.
why it becomes sour. When it becomes sour, that's
we explain that now.
Is it reduced because if gas is
No,
oxidized?
it's oxidized.
Oh, all right.
Oxidized. I mean, for me to show you, I can show you, but I have to bring it into some sixth form chemistry, right? But oxidation, all right?
Oxidation.
And when you form the ethanoic acid, you notice an additional oxygen was added, and oxidation is the addition of oxygen. That's all?
Yes, sir. Oxidate is one definition, addition of oxygen.
Addition of oxygen. You follow?
Yes, sir.
So oxidation takes place. I did not say it was a reducing agent or whatever. I said oxidation takes place.
Yes.
Right.
Somebody's asking if you can explain the fermentation thing one more time. They forgot about the yeast stuff. So just a general explanation.
All right, no problem.
They forgot about the whole,
All right, so you want to go from sucrose? Or this one, the glucose?
The last part, the last equation.
All right. So glucose is C6H12O6, the same structure as fructose. You put the sugar, which is glucose, we call it simple sugars, all right? But persons will do test for simple sugars. So this is a simple sugar. So sucrose in the flask, along with your enzyme, and the enzyme contain the zymase, all right? So the yeast contain the enzyme zymase. Clear? When you close it, you lock out oxygen, but some oxygen is inside. So I'm saying to you that the yeast must first respire aerobically, but it's not here nor there. You don't need to tell them anything about that. I'm just letting you know that O2 will be inside, but the yeast will respire aerobically first to use up that oxygen. Then it will respire anaerobically to produce the alcohol and carbon dioxide. You will see effervescence. The effervescence is when the bubbles come up and the gas comes through the delivery tube and it travels into the lime water. And we know that carbon dioxide with lime water will turn cloudy. You get a white precipitate. That is how we know that we are producing the alcohol. Then we said that if you produce your alcohol and you this alcohol it cannot be above 14%. So it's somewhere there, okay? Can't be above. Why? Because that percentage is toxic to the yeast or the enzyme. Hence, you can't produce a higher percentage. All right. If you stop now, it's finished now, no more effervescence, and you open the container and leave it open, then O2, which is oxygen, will oxidize the alcohol to form ethanoic acid. Okay? So this is a reaction of alcohols. Any alcohol or alcohols, well, not any alcohol, because you have tertiary alcohols and so on that cannot be oxidized. But I'm not going to primary and secondary with you either. I'm just saying that some alcohols can be oxidized, right, to form acid, the carboxylic acid or alkenoic acid. Okay? At the 6-pound level, we use O in a square bracket for oxidizing agent. So this will be doing the oxidation or the oxidizing of the alcohol to form the ethanoic acid. So this here would now form CH3COOH, and you could put the O in square bracket, or you could leave O2. Good. And a property of the acid is it is sour. So that's why you get that sour smell. Clear?
Why does it become cloudy again?
Cloudy because that's a test for carbon dioxide. We use lime water to test for the presence of carbon dioxide. So carbon dioxide, I want some space. Carbon dioxide in lime water, calcium hydroxide, produces calcium carbonate, which is a solid. So this is your precipitate plus H2O. Okay? Good. And remember that here, that the water, over there, with the water and the alcohol, they are miscible. Alcohol will dissolve completely in water because they have the same type of bonds, and the bond that is present is hydrogen bonds. Clear? So they are miscible. Good? How we say?
Looking good.
All right. Any other question? I'm going to go back now to my question. While I move, you can ask.
I think you're half time. Well, more than half time. So.
All right, good. So we can move down.
Yes.
Okay. So Gemina was presented with a flask that contains a mixture of diluted rum. Draw a labeled diagram of the apparatus she should use in the laboratory to obtain a concentrated sample of ethanol. So,
sir,
yes.
So you just draw the apparatus used in with the fractional column, fractional distillation.
Fractional distillation, yes. So that's the column. That's the one with the column. Yes.
And the fraction in beaker, the fractional column condenser, and the receiving beaker.
Well, you leave off something, man. Thermometer. Thank you very much. Thermometer. So you have the conical flask to collect and the heat. So the heat will be
and the Bunsen burner.
Yes. All right. Good. So you have the round bottom flask, you have your fractionating column, your thermometer, your condenser. Remember, make sure you know where to put water in and water out. It's important. Water in comes from close to the flask and goes against the flow of the heat. Okay. All right. If you put water in at the top, it is going with the flow of the heat. It will not cause condensation to occur efficiently. Are you with me so far?
Yes, sir.
No, you said no?
Yes,
yes.
Sir.
Okay,
yes.
So the water in must be, when you're looking at the condenser, must be from the lower end and it goes against the flow of the heat, which will remove more heat, causing a better condensation process. So this part would require that. All right, good. So we're good so far. All right, let's go to, this is now 2016. Number 3. Are you seeing something that is familiar?
Yes, sir.
Yes, sir.
All right, so go ahead quickly. Give me the definition.
All right, sir. So structural isomerism, sir, that is the existence of two organic compounds that have the same molecular formula and different structural formulas.
Yeah, all right, good. 2 or more. Okay? 2 or more. Don't limit yourself. 2 or more. Yes, you're correct. So same molecular formula, but different structural formula. Now, suppose you want to say different arrangement of atoms. Same thing. Okay? Clear? But I would prefer if we say different structural formula because not all the time, when you rearrange the carbon atoms, you know, sometimes you can move the functional group. So I prefer if you say structural formula instead of different arrangement of atoms. Clear? Are we good?
Yes, sir.
All right, go on, no. Talk to me about P.
Propene.
No,
Sir,
wait. State the name of P.
Pent-1-ene.
Yeah, man, pent-1-ene. The
Or
person said
normal propene.
No, man, you say propene because you can't be prop because prop is 3 carbons. How many carbons do you see in this structure?
5.
Oh, pentene.
Yeah. No, yes. But you have to say pent something. Where is the double bond?
Pent-1-ene.
Pent-1-ene.
That's correct, my dear. It's between the first and second carbon, also? I will go with a lower number. So pent-1-ene. All right. Everybody okay with the name of P?
Yes, sir.
Sir.
Good. State one physical property of compound P. One physical property.
Liquid. So it's a liquid.
Yes. Mm-hmm. What else? What else you could tell me?
Sir, is it unsaturated?
Physical.
Or
Well,
physical?
yeah, it is. Well, unsaturation is you could say physical, but the unsaturation will cause more chemical reactions to occur more than anything else. So I prefer if you not say that one. What? All right. So how many carbons do you see in it? How many carbons?
5.
5. So if you have 5 carbons and you have a container with pent-1-ene in it, and you have a pent-1-ene molecule against the next pent-1-ene molecule, would the bonds be strong or weak? Would the bond be strong or weak?
So can you repeat that question?
No.
All right. I'm saying to you, if you have a container with pentene in it, with pent-1-ene in it, so it's like a liquid, right? You say it's a liquid. So you have molecules of pent-1-ene moving against molecules of pent-1-ene. I'm saying the force of attraction between the two molecules or the molecules of pent-1-ene, would they be strong or weak?
So strong.
They be weak. Okay.
Can you explain that?
All right. So the more carbon atoms you have, so let's say I have 3 carbons. 3 would be weaker or lower than 5. Okay. 4 would be lower than 5. 5 is still low, but you would not say they are strong or the bonds are strong until you reach probably about maybe 10 going up. Okay. So anywhere between say 2, because it's alkene, 2 and say 8, 9 or so would have low, weak force of attraction.
You could also relate it to the state.
Yes.
Liquids, gases.
It's liquid.
normally.
Yeah. Yes. So I'm trying and share this thing here. Remember when I showed you alkenes, what did I say they were? I gave you alkanes and I gave you alkenes. What did I say they were? You remember? Anybody?
Unsaturated compounds.
Saturated and unsaturated.
What are their physical state? You remember the physical state?
Sir, they're oily liquids.
Yeah, they're liquid. Yes. Let me just show you. Not that. Same here. So this one is the alkane. So for the alkane, the first 4 are gases, and that's how we use them to cook. The others are liquids. So the gases will be lower than the liquids. You agree? But liquids are lower than solids. So let's go to the alkenes now. Where is it? Here we go. So we said that the first 3 would be gases. And these from pent 5 up are liquids. And then the more you go, the more carbon you add on to it, the force becomes stronger. And therefore, we're going to link now the force of attraction to the boiling point. Clear? Give a next word I could use if I want to discuss boiling point. A next word, anybody?
Sir, Another, no, I can't the V word.
Yeah, it is. It is.
Volatility or something.
Don't doubt yourself, miss. Yet it is the V word. What's the V word?
Volatility.
Volatility. Yeah. No.
Volatility.
Volatility.
Yeah.
Volatility.
Volatility. You're correct. Volatility. Got it? So listen to me now. The lower the boiling point, right, the more volatile you are. The higher the boiling point, the less volatile you are. Tell me if you're with me so far.
Sir, repeat that.
The lower the boiling point, the more volatile you are. The higher the boiling point, the less volatile you are. Miss, spell it for them for me in the chat, please.
Yeah, somebody did, but I'll write it again. But
Thank
just
you very
tell is how readily the substance can change into a gas.
Change from liquid to gas.
Right.
So that is why when I'm looking at volatility, I link it to boiling point. Clear? So you must be a liquid in terms to boil. So if your forces are strong, then you need a lot of heat to break the bonds to go to gas. You follow? So you are less volatile. But if your forces are weak, you require less energy to break the bonds to go from the liquid state to the gaseous state. Tell me if you're with me so far.
Yes, sir.
All right. So you could say another property could be then low boiling point, right? Or low volatility. Or you could say it's volatile. You with me so far?
Yes. Somebody gave the low boiling point in the chat.
Good, thank you. What about when you look at an alkene? Can you differentiate it from an alkane?
Yes, sir.
Yes, sir. The presence.
No. Mister, when you look, when you look at it, no
yes,
reaction.
Sir.
You can when you look at it.
Well, no. You need bromine water.
You need something to test for it. So that's a physical property. So what's the color of it? What's the color of it?
Color of what, sir?
Pentwanine. What's the color of it?
Colorless, sir.
Colorless. So that's the physical property as well. You follow? You could also add. I mean, that's fine. But are you understanding what we're doing here?
Yes, sir.
We're looking at the alpha one, but we have to give you more than one, just in case now the comments are right. Give me 3. You can give them at least 3. Clear? All right. Give me one property now of compound P, one chemical property. When you think of chemical property, what should you think about? Once you hear chemical property, what should you think about?
So it's very reactive.
The chemical reactions. Clear? So
Yes,
when alkenes react, what are some of the reactions you remember?
Addition.
Addition. Because an alkene, so it's unsaturated, so addition. Yes. What about, give me the next one. That's the same thing. That's the same thing as addition. So you could say halogenation or addition. Clear? The same addition of an halogen.
Combustion.
So, sorry. Halogenation is a type of addition. Clear. Combustion is another. Yes. Yeah.
Sir,
Good.
is it hydrogenation?
Yes. Well, that's also an example of an addition reaction. Because you have several types. So you have hydration, you have hydrogenation, you have halogenation. So if you're giving the specific one, go ahead and give the specific one. Fine. That's fine. All right, so we're good. Let's move on now. Draw the fully displayed structural formulae of compound P and one of its isomer. So what's compound P again, class? Remember? Pent1-ene. So give me the name of one. I'll just listen to you and we can. If preserving difficulty, I'll draw it.
Pent2-ene.
Pent2-ene, yeah. What else? What else?
Pent3-ene.
Pent3-ene. Let's check first. So we have 1, 2, 3. 1, 2, 3. We can count, 1, 2, 3, 4, 5. All right. So that's our structure. So you say 1.
Pent3-ene, sir.
Wait, no. That's how we're checking. We're checking, So this is Pent2-ene, right? You agree?
Yes, sir.
Yes, sir.
All right. But look now, if you say Pent3-ene, look at this now. You're saying this. you are assuming this, right? That's 5. 1, 2, 3, 4, 5. But look here, which side would you number from?
Sir, from the right.
From the right.
Yes, so this becomes what? So it's the same thing as this one. Make sense?
2 in, yes.
Yes, sir.
So these two are equal. Same things. All right, give me the next one now. Give me another one. So when you can shift the double bond, go to the carbon atoms and rearrange them.
Sir.
Sir, 2-methyl pent-1-ene.
Yes, sir.
All right. 2-methyl. Let's go with 2-methyl.
Someone has 2,2-dimethyl 2-propene.
3, 4, yes. All right. Go on again.
Somebody gave 2,2-dimethyl 2-propene.
2,2-dimethyl
2-propene.
No, something wrong with that. 1, 2, 3, 4, 5. You're correct in terms of 2,2-dimethyl, which is this one, right? So it's 5 carbons. So it's 1, 2, 3, 4, 5. So it's 2,2-dimethyl. That's correct. Your number from the double bond. So you go 1, 2.
So is it the longest chain?
Pent-1-ene.
Yeah, no, man. It's
so
prop.
is it prop, not F.
Prop, right? But again, remember, we don't have to say prop 1-ene. It's fine, you know, if you say it.
First I said prop 2. I mean 2 prop.
Right.
It's the same thing.
Remember now, it's carbon, so you go with a lower number. 1, 2, 1. So it's 2-methyl. So it's 2, 2. How many of them? 2 of them. So then it's methyl, and then the parent chain is prop. So you could say prop 1-ene or just propene, because if a double bond come here, so the same name.
Yes, sir.
Okay. All right, and this one you just told me was 2-methyl, and it's on the second carbon. It's 2 already. So 2-methyl bute 1-ene.
Bute 1-ene.
Bute 1-ene. Good. Thank you very much. I hope you can read my handwriting. Is it clear?
Yes, sir.
All right. Thank you very much. Let's go back then. So we're good then. So let's go back to where we were. Where is it? Where is it? Where is it? Oh, right here. All right. So we're good then. So I am sure questions like this will come back. All right. Compound P reacts with hydrogen gas in the presence of a catalyst to form compound Q. All right. Talk to me now about this one.
Sir,
what's the name of this process?
Hydrogenation.
Hydrogenation, sir.
Hydrogenation.
Yes, hydrogenation. Before I continue, let me say that you could do other types of isomers for the pent 1-ene, okay? Because you could do some where you do with the 2-ene, right? So you could do you can do several as long as you have the same number of carbons and number of hydrogen. That it matches each structure matches the molecular formula. So let me just say that from now. We didn't do all of them. All right. So we say hydrogenation. Draw the fully displayed structure. What do I do? What do I do?
So you're going to draw the structure when hydrogen is added to it.
So it does want them
so you're going to be a pentane structure.
Pentane structure. All right. So you drop. All right. So which one are we using? Pent 1-ene? Come up here.
Yes, sir.
Wait, so it says branch. So.
Oh, it's question the branch? Let me go back. 1 second. Draw fully displayed structure of one branch. Okay, of pent 1-ene. All right, good. And then now.
Not of pent 1-ene, of the product, which is the pentane.
Compound P reacts with. So P is pent 1-ene, reacts with hydrogen. Good. So you're gonna form now your saturated compound in the presence of a catalyst. So let's do that first.
And then
we're gonna draw a branch now for that.
Of
all right.
That
so
product, yes.
All right, good. Let's come back up here now. Muchas gracias. All right. So we have 1. Sorry about that. We have 1, 2, 3, 4, 5. Plus H2. What do I have over the arrow? What are we using?
Sir.
Is it phosphoric acid?
Sir, well, 300 degrees of heat, 70 atmospheres of pressure, and the H3PO4. Not sure if I'm getting that right.
You sound like you're giving me something like hydration.
Right.
Hydration.
Somebody's saying 200 and nickel catalyst.
All right, so it's about 140. But 200 cannot be high still. About 140 degrees.
150, yeah. Okay.
So 140, 150, maybe 160 around there, and nickel catalyst.
Oh, all right.
So we form, that's fine. 1, 2, 3, 4, 5. And look here, if you ask the person that I teach, I love the discussion. So I love when students talk back to me. Don't worry about making a mistake or getting something wrong. All right, discussion is what will help you. So this is, all right, give me the name of this one now. Oops.
Pentane.
Pentane, sir.
Yeah. So pentane. All right, so pentane is now saturated, okay? So now we need a branch group from this. Give me a branch group from this.
2,2-dimethyl butane.
All right, you love twang do. It's a 2,2-dimethyl. All right, come, methyl. All right, let's go. 1 year so, 1 year so. That's fine. Is that correct? Methyl. Put a H there, H there, H there, H there.
Excuse me, sir. So how is it bute?
Sir,
how is it bute, sir? And bute?
No, wait. She said bute?
Yes, sir.
It should be propane.
Probe. Because look at the structure in my head, I seen a probe, so I didn't hear the bute. Sorry. So this is pentane. All right. So you're moving two. So you're moving this one and put it here and here. So
Sure.
this is 2,2-dimethyl propane. Yes. Give me the next one, please.
So could you use which is a different one, sir? Is that one ethyl propane? Is that
No,
one?
you can't. No, if it's a one, all right. What you're telling me is this. This is what you're giving me. 1, 2, 3, 4, 5. But this is not possible. This is the same as this.
Yeah, same.
It's just
same
the orientation.
Some
Same
straight
thing.
chain.
Yes.
Oh,
So what I want you to do is to move one of the N carbon and make it into a branch.
Somebody's given 2-methyl butane.
Yes. Yes. Let me make sure now. So it's parent is 1, 2, 3, 4, and this is on the second carbon. So yes, 2-methyl butane. Good. Thank you.
I don't understand how the first one is propane.
Propane. All right. Let's go again.
Pentane, sir. The one to the left.
This is pentane. This one. This is
No,
pentane.
sir, the one below it. What is it?
This one is 2,2-dimethyl propane.
Oh, sir, I thought you said pentane. That's why
Oh, miss. I know I have a lisp, but my lisp, I mean, sometimes the son I say something else, okay? But it's not propane. It's not pentane. It's propane. So 1, 2, 3. Any other questions? We're good? And this is correct. Can we go back now?
Can I just put the name on that just so that we don't have any questions?
Which one?
On the third one. Yes, the last one.
All right. So this is 2 because the branch group is on the second carbon. So 2 hyphen. It's a methyl group. And the parent now is bute. And it's alkane, so butane, 2-methyl butane. And these are isomers of pentane. So everybody should satisfy CnH2n plus 2. Okay? So there should be C5H10. That's all?
12.
12. See? Boy, I can't. I'm teach chemistry. We've got to do some maths, miss. Sorry about that. All right. Let's continue. The 10 would be for the alkene, which is the unsaturated one. All right, so we're okay with this part. We're good with this one, class?
Yes, sir.
All right, give me a physical property now. Think, people, think. Think. We just did some for alkenes.
What's compound Q again?
Q is the isomer.
The isomer.
Wait, no, let me look.
Pentane.
The pentane, yes. The product. The product from P, yes.
Pentane.
When you add the H2. So give me a property, physical property.
Low melting and boiling point.
Yep. Give me the next one.
Sir, a low volatility.
It's a liquid because it's pent, so liquid.
Yes, sir. Can I just substitute that and say volatility, low
Yeah,
volatility?
man, definitely. What about colorless?
Yes, someone gave us in the chat.
In the chat? All right, thank you very much. Good. So that's good. All right, look, let's do D. What type of structure is D?
Pentanol.
All right, hold on there. Somebody say wait.
Yes, sir. He adjusted low or volatility for pentane.
Yeah, man. Volatility. Would you say volatility? It would be low as well.
Low.
Yeah, man.
Okay.
Sorry, should be high. Should be high. Should be high. Should be high.
Yeah, I was saying it should be high because like it would
High
be
volatility.
Yeah.
Yeah, because it will readily change into a gas.
Just a make sure, miss.
No, sorry. Oh, but I thought it said boiling point. Okay, the boiling point is low. No, but if the boiling point is low, the volatility is low.
No, man, high. Remember you had explained how readily, if they can.
Oh, the ease with which it go from high volatility. Sorry. Yes. Sorry about that. Yes.
Right.
Sometimes the brain get mixed up, Take time with me here. Yeah, man. Thanks for the correction. That's correct. All right. So we say high volatility. So again, let's go again. Low. Write it down for me, please. If your boiling point is low, your volatility is high. Okay. If your boiling point is high, your volatility is low. Good? We have that now?
Yes, sir.
All right. Muchas gracias again. Look at this now. Somebody give me the name for this. What's the name again?
Pentanol.
Pentanol. 1, 2, 3, 4, 5. Not quite.
Sir, pen to 1-al.
Not quite.
Pen to al.
Pent 2-al. Pen 2-al, yes. Or 2-pentanol. Because this one is coming from it's not on the first carbon, it's on the second carbon.
Sir,
yes.
Sir, isn't the nomenclature for it penta 2-al and not null-al?
I said pentan. I said pentan 2-al.
Oh, pentan.
That's the first thing I said. Pentan 2-al or 2-pentanol.
All right, sir.
Yeah, man. Just make that's fine. Just make sure so you hear what I'm saying. All right. So if I say something different, I can always correct myself. Clear? So nothing is wrong with that. So pentan 2-al or 2-pentanol. All right. You understand why it's 2-pentanol or pentan 2-al? Everyone?
No.
All right. Let's go.
Carbon.
Let's go back to the whiteboard. So we have 1, 2, 3, 4, 5. Let's call it pentan. So this would be pentan 1-al or pentanol. Clear? So in this case, we are shifting the functional group. So shifting the functional group is a type of polymerization. It's a type of isomer, not polymerization, a type of isomer. So now I go from the first one, 1, 2, 3, 4, 5, from the first one to the second one. And could I go to the third one?
Yes, sir.
I could, yes. So pentan 1-al, pentan 2-al, pentan 3-al. These are all isomers. You understand now?
The person who asked her to do it over.
You okay with that now?
Yes.
She said yes? Okay, all right. Let's go back here. So state the name of compound R, and we just did that. State the conditions required for dehydration of ethanol. All right, let me see.
Sir, concentrated sulfuric acid.
And?
Is it 180 degrees Celsius?
Yes, heat at 180. Now you could say 180, 170, 175, anywhere within that range between 170 and 180. Give me the next one now. The gentleman was saying something else. Go ahead.
Oh, yes, sir. I was just going to say a change of heat, which I think I have 170.
Yeah, man. So the 170 would suggest the heating. Or what's the next condition you could use?
Sir, I could use aluminum oxide.
Well, yeah, it can be used. It's called activated alumina. Yes, that can be used. Yes. And 450. That's the condition. But at this level,
yes, sir.
We hardly use that one at this level, though. We use mainly the phosphoric acid with the silica catalyst. Right? I think the pressure is 300. And the thing is
Yes,
60 atmosphere, I think.
360. Hold on, let me check.
Yes.
Or 70 atmosphere, sir.
I think it's merely 60. 60. But 60 or 70 is close enough. So it's phosphoric acid, 300 degrees Celsius and 60 atmosphere. Okay? And I think it's in silica catalyst. But you could just say concentrated phosphoric acid. All right? How we stay so far?
Sir, you also add silica to your, sir. Silica as a catalyst.
Yes.
Wait till I for the conditions.
Yes, for the condition. You now write them over the arrow.
Sir, with this PowerPoint, sir, with this PowerPoint be available?
It's not a PowerPoint. It's not a PowerPoint, you know. It's just a question I'm running through with you.
Sir, the part that you had the list with the
Yeah, man, you can get it. Not a problem.
Okay, sir.
I did not complete it though in terms of macromolecules, but you can have it, no problem. All right, where are we now? So we go so far? So we know the conditions. So this is what? Dehydration, right? So you are removing two things. What are we removing? When you have dehydration?
Sir, we are removing the water out of it.
Yeah, well, yeah. When I said two things, I meant you take off H of something.
Hydrogen.
And OH. Yes.
Hydrogen and yes,
yeah. So when you dehydrate alcohols, what do you form?
They're alkene.
Alkene.
Yes. So the opposite must be true. Is it? Is the opposite true?
Sir.
So when you hydrate alkenes, what do you form?
Alcohol.
Yeah.
Alcohols.
Yes. And we use the same condition for hydration, for hydrating the alkenes. All right.
Sir. Can you state the conditions? No, everything in one.
The condition for which one?
The one that says state the conditions required for the dehydration. Yes, sir.
All right. So far, all right. All right. So we're going with for the first one. You're dehydrating alcohol.
Dehydration.
Dehydrating, or so the process is dehydration. You are dehydrating your alcohol. Right? You can use concentrated sulfuric acid and 180 degrees Celsius. The 180, it could be 180 or 170, or you could say 170 to 180.
$170 or 178 of
No,
what?
170 or 180. Or a range of 170 to
right, it's a range.
The range of 170 to 180. So if you give anything within that range, you're still all right.
Of what, sir? Yes, and 170 to 180 of what?
Oh, degrees Celsius. That's the temperature. Sorry. Degrees Celsius. That's the temperature. So now the other one now is phosphoric acid. You could use phosphoric acid. H3PO4. And it's normally used with a catalyst, silica.
Sir, because they're strong dehydrating agent.
Yeah. So that's when you're going from, well, hydration and dehydration, the mechanism is pretty much, it's kind of similar. But I can't go through the mechanism with you at this level because it will confuse.
All right.
So when you reach
the sulfuric acid would be the dehydrating agent.
Yes. But again, remember, I say for both hydration and dehydration, we use the same condition. Okay. So you have your water along with the sulfuric acid and the heat. And the water will be in the form of steam. So the same conditions. So let me add the other part of the phosphoric acid one. The temperature we said was 300 degrees Celsius and 60 atmosphere. That's the pressure. 60. Have that? All right. So we reach one. We reached 20.
Sir, what is 300 degrees?
Yes, Celsius. The temperature. So similarly, like how we say when you the hydration and dehydration. So hydration of your alkene forms your alcohol. Dehydration of your alcohol forms your alkene. It's similar to alkene forming alkane. Okay. So alkenes, when you add the H2, you form your alkanes. You can do something now to remove the H2 to go back to your alkene, but we're not doing that one at this level. All right, so we finished with 2015, 2016. Let's go 2017. How we stay? Are we okay, everyone? Anybody lost? Anybody don't understand anything at all? Anything you want to go over? Anything you want to discuss? Talk to me, please.
Sir, question.
All right, one at a time. Let me hear from Antoine.
Mm-hmm.
So let's say in the exam, if you get some of the conditions, is it okay if you just put high pressure and high temperature?
No, they want specific temperature and pressures. You have to give them the specific temperature and pressure.
Wait, so we can't give like a range right of the temperature.
No, temperature can give the range as long as you are within the range. Like for example, 170 to 180. If you give 165, you'll still get the mark. As long as it's not way out.
Oh yeah.
Make sense?
Yeah. I don't know if you're wrong. I heard something about 300 degrees Celsius.
I hardly can hear you there. You're breaking up really bad.
I heard something about 300 degrees Celsius.
300 degrees Celsius?
Yes.
Yeah, man, that's the one for the phosphoric acid and the 60 atmosphere.
So they have 170 to 180 degrees Celsius and 300 degrees Celsius.
No, it's one or the other. It's 170 to 180 degrees Celsius with concentrated sulfuric acid. Or phosphoric acid in the silica with the 300 degrees Celsius and the 60 atmosphere.
Okay.
Make sense?
So the first, so we don't need to put all of them, then we can just put
one or the other. Yeah, one or the other. Yes, nothing is wrong with that. Just like how if I say, tell me how you could test for unsaturation. If some of you use bromine vapor or bromine liquid, right? Some of you might use aqueous bromine water. Again, I have a problem with that because you should form bromo alcohol. But again, because it's at this level, I won't argue with it. So bromo alcohol is what you form, but you're gonna form some BR, but that's a minor product. So that's okay. So you could use that, or you could use the potassium permanganate.
Permanganate.
Yes. So we're not saying everybody must do the same thing. Once you get the things and you know the reactions and you have options, anyone you give is correct. Clear? Are you okay?
Person who asked for the clarification, are you okay?
Mm-hmm.
Oh, sorry. Okay, so for one condition, I could just put concentrated phosphoric acid and 170 degrees Celsius to 180 degrees Celsius.
No.
Concentrated sulfuric.
Sulfuric. Concentrated sulfuric. Yeah. And 170 to 180. Look here, when I'm smiling, I'm not laughing at you. You hear me, miss?
No, it's okay.
No, I just want to make that clear. I'm not laughing at anybody. It's just that, you make me happy. That's all. Yeah. Let's move on. All right, we reached number 5 in 2016. Look at methane. Methane CH4 is the simplest hydrocarbon known to man. Identify the type of bonding present in methane. And say the reason why.
Covalent, sir.
Yep, covalent bonds. Yes. What's the reason why?
And this is because the elements that are composed, or the elements of methane are carbon and hydrogen, which are non-metals.
Non-metals. Want to hear covalent bonds? Yes. Yeah, you're correct. But once you hear covalent bonds, you think of non-metals. And you were
And
saying something
so,
about gases. Go ahead with the gases now.
yes,
You were saying
sir. They're gases, so they share our
Mhm.
electrons.
Simple molecules.
Yes, sir.
Yeah, man. Good job. Yeah, full marks, man. Full marks. I would give you full marks for that. All right.
Right, sir. So now for mentions, like a carbon can only hold 4, so it's a complete.
Yeah, it did not ask for that.
Also,
It just say identify. And look here, people. Listen to me. I like the question because now I can tell you right now. Whenever you're in the exam, I have the exam paper. Take a pencil and identify the action words. What are they asking you to do? Underline that and then do exactly what they want. Don't give them anything extra because you're gonna waste time doing a lot of unnecessary writing. Am I making myself clear?
Yes, sir. That's all.
Yeah. So if you say
You know, sir,
identify, go ahead.
No, sir, cause like sir, yeah, I kind of paranoid, sir, not the exam and like no.
You just want to make sure they did the right thing.
Yeah, but that's, yeah.
Yeah, I understand. But you don't want to waste time, clear? Because
yes, sir.
if you write a million things, they're going to mark what they're asking you for. So they're going to look for it, going to read through and find. And if the answer is not in it, all the writing you're doing will be in vain. I hope that's clear to everybody.
Yeah.
All right, good. So we say covalent bonds and you state the reasons why. Look at methane now, part B. All right, methane, like other alkanes, is generally unreactive. Anybody can tell me why alkanes are unreactive?
Sir, because the presence of the strong double bonds.
Yeah.
Strong single bond.
Yes,
sir, they're saturated.
They're saturated. Thank you very much. However, under certain conditions, who can tell me the condition now that you need? For
UV light.
UV light. All right.
UV
so
light.
notice, when I start looking at no questions yet, we're just making sure we understand. Would you need UV light if you are reacting a halogen with an alkene?
Yes,
no, sir.
No, you would not. Because the UV, what's the purpose of the UV light?
Sir, if we increase the
The rate
temperature.
of the reaction as well.
Activation energy.
Well.
Yes, sir, rate of reaction. I'd use rate of reaction.
To provide energy to break the
or
bonds.
to offer energy to break and bonds and allow them to collide more.
Which bond is gonna break?
The covalent.
Initially.
The carbon.
Yes, no, not the carbon. Let me show you something. 1 second. Just want you to understand this so you don't make a mistake with it. Look at this. 1 H. And this is Cl and Cl. Clear? You see, the UV light is important to break this bond first. So you form what is called a radical. And this is now what's going to cause the reaction to continue. Okay? So the UV light is important to break the halogen bonds to form a very reactive species. Now, I'm not going to go into any mechanism with you again, because this is, again, sixth form. So once you break this, you form something that's very reactive. Now, what's going to happen, class? This will come now and substitute one of the H's here. Not true? There's 2 of them,
yes,
you know?
sir.
Yes, sir.
Yes.
But now, with the H that was removed, gone, where they?
To go form hydrochloric acid.
All right. No, it's going to form hydrogen chloride. No, don't confuse yourself now, miss. HCl aqueous is hydrochloric acid. HClG is hydrogen chloride. In this case, it's this one. Clear?
Yes, sir.
So this now is one reaction would be now HCl. Okay? But the question is saying that now we're gonna continue. So we're gonna have more of this, removing more of the H's until you end up with C, Cl, 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 Cl.
Tetrachloromethane.
Yes. All right. Or carbon tetrachloride. All right. Or what you say is also okay. All right, people. Let's go back to here. Now, go ahead now and tell me what to write down for my balance equation for reacting CCl4 with Cl2. What?
CH4.
Wait, let me.
CCH4.
H4
plus
Cl2 produce
arrow. What about my UV light?
UV light.
Okay, don't forget that. Produce now Cl what?
Cl4
4 plus
HCl gas.
HCl. All right, gas. All right. No, is it balanced?
No, sir.
No, sir.
No, sir.
All right, so let's balance it.
Sir, put
For
that
hydrogen.
There are 2 at the HCl.
2. Yeah,
At
yes,
2
sir.
for
Put
the
that 2 at the HCl for 1.
2 or 4?
4.
4. Okay. Okay. And then
then put a 2 at the CL2, sir. At the crack.
2 at the CL.
To be 4 at the CL.
Well, no,
4, man.
4. A 4, a 4.
Yes, 4. And you can check now to see if it's balanced now. All right. Always say, because this is 4 CL is 4 and 4, no 8. 2 4 is 8. Okay,
Yes,
1 CL, 1 CL, and we have 4 H's. Yes, so that's
Yes,
balanced.
sir.
Good. What if they wanted a monoproduct? So what they say they want a monoproduct. They don't want the full substitution or a dye product.
Sir, it would be H3O. You don't want the
All right.
product.
Yeah, man. Yeah. Give me the mono one.
It would be CH3.
CH3.
CH3Cl.
CL. Yes. Give me a dye product.
CH2Cl2.
Beautiful. Beautiful. And you can figure out the rest. That's what I'm interested in right here. Always stay. We're good?
Yes,
Eh?
sir.
All right.
Yes, sir.
Again, I'm not laughing at you. No, I'm laughing at you because you're doing great. State the type of reaction taking place and identify the reaction conditions. What's the type of reaction?
Substitution.
Substitution. And what's the condition?
UV
light.
UV light.
UV light. Yes. Now, if it's a light, I mean, I think let's still give it a mark, but please use UV light. If it's a sunlight, UV light is sunlight anyway, so that's okay as well. All right. Let me see. Okay. Now, let me see if you're thinking. Identify and draw the structural formula of alkene and the acid from the list below. All right, let's not do that. Tell me what each of them is.
Sir,
The first one is alkene.
First one is alkene.
Alkene. All right. This one is alkene. This is
Alkene.
Alkene.
This one is
acid. Alkalic acid.
Alkanoic acid or carboxylic acid. Yes.
Carboxylic acid,
And this
and
one
that
is
alcohol.
alcohol. Yes. And guess what? You can always check them using the
General formula.
General formulas.
yes. All right. All right. All right. So let's move on. Oh, so you identified them already, so no problem there. Yes. For each of the following that. Okay. Look at D now. For each of the following pairs of compounds, identify a test that could be used.
Sir,
Bromine water.
Permanganate.
All right.
The
Yes.
acidified potassium permanganate.
Yes. Acidified potassium
permanganate.
Potassium permanganate.
Or the potassium dichromate, sir.
Or dichromate.
7.
Mainly though, because
6.
the dichromate is a weaker oxidizing agent, you use mainly the permanganate. But it can be used, but it's a weaker one. So I would not so stick with the bromine or the permanganate. Fair? I mean it can be used because it's not a big deal. It can be used. So you can use the dichromate, the permanganate, or the bromine water. Now listen to me now. We say bromine vapor. You can use bromine vapor, bromine liquid, and the bromine liquid. All right, let me say this to you. Halogens need what is called a carrier. So bromine liquid, let me go to a blank page to show you. Bromine liquid is bromine in something, that's Br2, in, like, let's say CCl4. So this is the carrier for this, okay? Bromine water is the same thing. It's Br2 in H2O, okay? So you have bromine liquid. So when you see bromine liquid, think of this. When you see bromine aqueous, think of this. But what I'm saying to you, it's okay now to say Br is added across the carbon-carbon double bond to test for the difference between it and the alkane. However, I'm saying to you, it's not truly correct in the sense of the word because bromine aqueous really should form a bromo alcohol. That's a major product. Again, because of levels, I'm not gonna make a big deal of it. Okay? Are we clear, class?
Yes, sir.
So bromine, aqueous bromine should really form a bromo alcohol. All right. So it just in somebody mic, somebody speaker. Mic, please close the mic a little bit. In the event you see bromo alcohol and bromine aqueous, don't be confused, okay? But it's okay if you put BR. But that's really a minor product for aqueous bromine. So it's the liquid one or the bromine vapor should really give it a BR across the whole bond. Again, not gonna make a big deal out of that. All right, let's go back to the question. How do you feel so far with the questions we're looking at? You feel like we're making progress?
Yes, sir.
All right. How can you differentiate between your that's the question, right? Yes. Identify or distinguish between the two. All right. So we're okay with these two. Think about the class. How can you distinguish between your alkane and your carboxylic acid?
Sir, so would you react it with like a base? I'm not sure if that's the right answer. Because a reaction would be seen with the carboxylic acid. So like if you reacted it with sodium hydroxide.
All right, yes.
It's a reaction.
So you could react it
with alkane.
Yeah, I agree. So you could use a carbonate. A base, acid and base give you a salt and water. All right, let me not say a base per se, because you want something to prove, to show you that something is happening. So a carbonate would give you more effervescence, not true?
Yes.
Than just a regular base. All right, so say carbonate then, because you get effervescence. So you could use a carbonate or a hydrogen carbonate, because the effervescence will prove the difference between the two. Is that making sense?
Yes, sir.
All right, but what about litmus paper?
Oh, blue litmus paper.
Yeah, man, blue litmus. Yes.
Turns it red.
Right. Mm-hmm. All right. What about adding it to some water? Solubility.
Sorry, Christian.
Yeah.
But when they say blue litmus paper, we're not gonna end up using two reagent.
Two reagent. All right. Most times when we use litmus paper, we use both. We use blue and red, and one react and one react. In this case, we know that nothing will happen with one, because if it works with, if the blue litmus paper change to red, right, because of the acid, the alkane it has no free H+ ions in it to be acidic. You follow? So that will be no change for that litmus paper. So in this case, there's no need to use the other one. If you get my drift.
Yes.
Am I making sense?
Yes, sir.
Yes, sir.
All right. So what about solubility?
Sir, the alkane would dissolve and the carboxylic acid will float.
Think about it. Think again. Come again.
I was saying that the acid would dissolve and the
acid
alkane
would dissolve.
would not.
And the alkane, no. So the carboxylic acid, it itself contain, again, what the word we used earlier was hydrogen bonds. So, and remember, the acid part of the acid group is kind of ionic. It's ionic, right? Let me show you. So CH3COOH, okay? So when you put acid in water, don't it ionize? Isn't it a weak acid?
So it not complete.
Yes, sir. It will partially ionize.
It's partial ionization. But this is a small acid, so it will dissolve, right? The main thing why it will dissolve completely is because of the presence of what we call high
the hydrogen
bonds. So when the bonds are similar, things will dissolve. So this part you could say ionic. So water is polar, so it will dissolve in water. Or you could discuss it from the end of the hydrogen bonds. The alkane, was it alkane? Was it alkane?
Yes, sir.
We're comparing the two. The alkane, look at this now. With this one, you can say, okay, one side is negative and one side is positive, right? One side is negative, so this side is positive up here, so down side, right here, so it's a negative side. So it is polar. You can't find a negative and a positive side on this because of the equal distribution of charges around the carbons. You see that? You see that, class?
Yes, sir.
So this one we say is polar, while this one would be non-polar. Hence, if you are non-polar, would you dissolve in water?
No, sir.
No, sir.
No, sir.
This is where now you'll have the water separating from the ethane.
Sir,
So
it's a
they,
question.
so they're not miscible. Yes, go ahead.
Sir, so all alkenes are nonpolar?
Alkanes and alkenes. Yeah. Well, for the alkenes, it depends on the symmetry.
So what do you mean by that?
But symmetry, all right, let me show you. I don't go too far in this, how would that? Is that Daniel?
Don't go there.
Well, let me just show him symmetry, miss. So this one you could say is symmetrical. You agree? Symmetrical. But this one, no, let me do this one. Let's make this one better. This one is symmetrical. This one is asymmetrical. You see it?
Yes, sir.
So we're not going into that. But we're looking at the alkenes. Look at this one. No matter the type of alkene you have all H's around. So you don't have any one side being more negative than the other. So we say alkanes are nonpolar. The alkenes that we work with would also be nonpolar, so they will not mix with water as well. Clear?
Yes, sir.
All right. So solubility is another test that you could do. If you add it to it, if you see two separate phases, it means that it is not soluble in the water. All right, we're good? We're done. This is 15 also. That finished.
Yes, sir.
2017 now. All right, 2017 number 3. Wait, this looks familiar, not sure.
Yes, sir.
Wait, was this 2016 or this 2017? Let me look good.
Sir, I'm sure the last
Is it-
one was 27. Was it? Or 2016?
It's 2017. No, this was 2015, 2016, 2017. But sometimes the questions look like, it's the same thing, but it's not the same thing because earlier it was pent 1E. Now they give us pentane. No, so 1, 2, 3, 4,
Yes,
5.
sir.
It's a different one, yes. Good. So let's run through now quickly. We can run through.
So it's an alkene.
Alkene.
All right. Yes, I agree.
Formula.
General formula.
C5.
Hello.
H2N plus 2.
All right. Hold on there. Note now. It didn't ask for the actual structure or formula. It asked for the general formula. It did not ask for the actual molecular, the molecular formula. You follow? So don't confuse general formula and molecular formula. So when they say general, they want the CN, H, whatever. We're good? We're good so far?
Yes, sir.
Yes, sir.
All right. So
Yes,
that's
sir.
so what's it? What's it? See what? CN?
H2N plus 2.
Uh-huh. All right. And give me one use of P.
Can
Use
we
as
use
fuels.
fuel?
Fuel. All right. Okay. I agree.
Sir, what is it? Propane, sir?
Yeah. Yeah. Pen.
No.
One, 2, 3, 4, 5. Pent, not prop.
Pent. Okay, sir.
But prop would also be a fuel. Heating. This one is
fuel.
more like a liquid that you burn. Clear? Yes. Look here now. Look here, class. Look here. Define structural isomerism. Come on. We're moving on. Come on,
The
class.
occurrence of two or more
Hello.
organic compounds with the same molecular formula.
What?
Different structural form.
Different.
Moving on. But that's my tell if you're right or wrong. Cause you're right. Moving on. Isomer of compound P. Pentane. Isomer of pentane.
Sir, you have two.
Sir,
Di.
No. Sir, 1-methyl butane.
No. You say one. You keep saying one. If you say one, it's a part of the parent. So a branch.
Two,
A branch.
sir.
Would have been one.
2,2-dimethyl butane.
No.
Sir, wouldn't it be like 2-methyl butane or
All right.
2,2-dimethyl propane?
Yes, you are correct. Yes, thank you. So look now, class. Look here now. Let me help you with this one. You say 1, 2, 3, 4, 5. You want a branch. If you get a straight chain and you want a branch, you go 1, 2, 3, 4, and then shift the last one and put it somewhere. You follow?
Yes, sir.
That makes sense? Then if on the next one, you go 1, 2, 3. You have that already. That was there. Shift the next one and put it at the next branch. Okay? So this is your 2-methyl 1, 2, 3, 4 butane. And this is now 2, 2 hyphen dimethyl propane. Good?
Sir, you can say 1, 2, 2. 1, 2 propane.
Well, you can't say 1, 2 because the 1 will be on the parent. You follow?
No, sir. Like if you put the bottom one and the first one, first carbon too.
This one on the first carbon? This on the first carbon?
The one that is propane, sir.
Oh, this one. Put it where?
Yes, sir. If you could have put this carbon on the first, yes, sir.
Then all right,
One,
look now.
two,
So you
that's
get
one.
1, 2, 3, 4, and that's a C. Isn't this the same thing as this?
Yes, sir.
So that's not an isomer. If you do this one, you can't do this one. Get me?
Yes,
In other words,
sir.
you can't have these two as two separate structures. They're the same things. All right, so yeah, you have to practice those. All right, let's go back. Let's go back because we can move a little faster now because of you guys are seeing that the things are pretty much, once you understand certain basic concepts, the same thing. Look at Q. Compound Q has the condensed molecular form.
Ethanoic acid.
Yes, sir, because it's a carboxylic acid.
Yes, so give me the name again. Give me the name of it.
Ethanoic acid.
Ethanoic.
No, man, you can't say, you see? Hello. Last time, were you here the last time?
Propanoic acid.
Thank you. Remember, I tell you, say the carbon in the functional group is a part of the name. Don't forget that. Clear?
Propanoic acid.
So it's propanoic acid. All right. Would compound Q be soluble in water?
Yes, sir, because it's
Yes, sir.
because
So it has the hydrophilic part of it.
Ooh, all right. No. Hydrogen bonds.
hydrogen bonds. Yes, sir.
Yes. So either say it's polar or you say because of the presence of hydrogen bonds. Clear? You good? So if you say polar, water is polar. Not true?
Yes, sir.
All right. And if you say hydrogen bonds, water also has hydrogen bonds. And once you have similar bonds, it will dissolve completely. All right, look at 2 now. What is 3b part 2? In the solution of compound Q, is the solution of compound Q acidic or basic? State a reason for it.
Acidic. It will change blue litmus to red.
And also say it partially dissociates in water.
That is what I want to hear.
Yes, it partially ionizes in water.
Hold on one second. You saying it is what? It changed something with litmus paper. That's a test to see if it is acidic. You follow? So you have to explain that carboxylic acid, when ionized, when it is ionized, it releases H plus ions.
Oh.
The H plus ions is what makes it acidic. So look at Lard. What's the difference between a strong acid and a weak acid?
A strong acid has all
the ease of ionization.
A strong acid would completely ionize, while weak acid would
what ionize
partially
mean?
ionize.
What the ionize mean?
Oh,
It releases a lot of something. Not true?
Yes, sir.
So the strong one releases a lot of H plus ions. The weak one releases a small amount of H plus ions. You with me so far?
Yes, sir.
Yes, sir.
Don't confuse strong and weak acid with concentrated and dilute acids, okay? Okay? There are two different, the concepts are different. So strong have to do with the ease of ionization. Either you're completely ionized or you're partially ionized or dissociates, any one of the words you prefer, okay? The strength of an acid now, no, not the strength, the concentration now has to do with the amount of water. Not true? The amount of water. So you can have a strong acid that is diluted and a weak acid that is diluted. You can have a strong acid that is concentrated and a weak acid that is concentrated. Tell me if you're following that argument.
Yes, sir.
All right, good.
Can you repeat, please?
All right, which part? Which part you want me to repeat?
There's part about strong and dilute.
Okay. Oh, all right. Strong has to do with the degree of ionization or degree of dissociation. Tell me if you're okay with that.
Yes, sir.
So a strong acid will be completely ionized. A weak acid will be partially ionized. All right? But I'm saying the strength and concentration are two different concepts. So a concentrated acid can be strong as well. So it can be strong and concentrated. Not true. Or you can be what? You can be a strong acid as undilute. Because the strength of the acid, the concentration has to do with the amount of water present. Clear?
Yes, sir.
So when I hear strength, strong or weak, degree of ionization, when I hear concentrated or diluted, the amount of water present. Plenty water, you're diluted. Little water, concentrated. Good?
Yes, sir.
All right. Part 2. Is the solution of compound Q acidic or basic? State your reason. Oh, you did it? You did.
That's
Hey.
what we did.
Sir just said that.
Sorry, my brain. Sorry. Part C. Compound R.
Butene.
All right, now look now. They give you one compound to form S. So state the expected change, which you just did. Now, what would you draw for the formula?
Sir, would add on the BR to it, sir. So would that be an alkane plus the BR?
Where would you put the BR?
On the one, the first and the second one. So would that be
all right,
1, 2.
across the carbon-carbon double bond. So anyway, double bond is, you put the cross here. So one here and one here. Let me go to the board to make sure everyone is following. Hold on. So it was bute. Lie. All right, so it was this, right?
Yes, sir.
Plus BR2. I don't remember if they said gas or liquid or aqueous. All right. And now we say we go BR that. Where the double bond was right here. So you're gonna add the BR now right here. You see it? Anybody want to attempt naming this thing?
Sir, can I?
Yeah, man.
2, 3,
Alright, sir.
dibromo.
Hold on, little miss. Let the gentleman.
Sir. 2, 3 dibromo butane.
Yeah, 2, 3 dibromo. 1, 2, 3, 4. Yes.
Butane.
Yeah. All right. We normally call these things halogen alkenes. All right, but again, don't worry yourself about that. Let's continue. So we'll finish with this now, people. So quick, we'll run through this. I lie. We do part 5 already? This was part 5? Number 5?
Nope, that was number 3, sir.
Oh, Jules. Jeez, I thought that was number 5. Sorry. All right, let's go to number 5 and then we run through the rest. All right. So this is gonna be the last one then, class. Or you want to continue?
Who want to continue?
I can continue.
So who want to go can go then. That is what you're saying.
Sir, exam
Yes,
at
sir.
goodly 2 weeks from now, sir.
All right, miss. Let's go then. So reach number 5, right? El Dorado. I'm sure you've heard about this rum. I've heard about it.
Yes, sir. Caribbean rum.
Appleton and Cockspur are a few few of the famous rum brands of the Caribbean. The main processes of rum making are fermentation and distillation. And we discussed already that when you get about 40%, to get a higher percentage, you must do distillation. And that's where you get the overproof or so. All right, describe the process of fermentation, including your description, the starting material, the role of your yeast, the reaction conditions, and a balanced one now. You notice this one now? So when they ask for one equation, give them the one with glucose forming the alcohol and the carbon dioxide. Tell me if you're okay with that.
Yes, sir.
Yes, sir.
So go ahead now. Give me the starting material.
The starting material will be sugar.
C6H12O6.
Starting material.
Sugarcane.
Sugarcane.
The sucrose.
Sugarcane. All right, sucrose. Fine. That's sucrose is a part of sugarcane still. All right, fine. But notice that they say the main. We're looking at the manufacturing of it from the the rum and thing. So we're starting from the sugarcane. Sucrose is fine. I think you'll get the mark still. All right. So sugarcane, sucrose. What's the role of the yeast?
Sir, to provide the enzyme zymase.
All right, to provide the enzyme zymase to catalyze the reaction.
Yes, sir.
The fermentation.
Catalyst.
All right, good. Is it only zymase it supply?
Sir, yeah, we know of.
Sir, the one before that we had used invertase.
Invertase, yes. Invertase. Yes, yes. What would be the condition now?
Cannot is in the dark.
No, in the dark. Why does it be in the dark?
Says so that the light doesn't denature the enzymes.
You see, if you say in the dark because you don't want sunlight to come and heat up your stuff, then that would be different. Because you want to be close to room temperature as possible. So maybe say between 25, 26, 27, anywhere there.
Yes, sir. Cool area.
Yes. So anywhere between 25 and 35 degrees Celsius would be fine. All right.
Yes, sir, because we don't want the heat to denature the
all right. Good. So if the temperature is too high, that will denature the yeast or the enzymes. You're missing out something though. What else? What's the major part you're missing?
So anaerobic respiration.
Anaerobic respiration or anaerobic conditions. So without oxygen.
Without oxygen.
Yes. So if you say anaerobic, fine. Without oxygen, fine. Any one of them you choose, you will be fine. Okay. All right. So what is the balance equation now? What's the balance equation?
So we use the glucose equation to form the ethanol and carbon dioxide. Right?
Yes. And you have that already. Good.
Yes, sir.
All right. Good. And let's move on. I hope when exam come and you see these things, you just start smiling. Now, what I need you guys to do, because I don't think I'm going to be able to do everything, you go and do some condensation practice and ask your teacher questions, okay? Okay? So you're comfortable with that. Also, saponification. That's the next thing I want you guys to pay attention to. Saponification.
Soap making.
Yes, soap making. Yes. And the hydrolysis of your ester. So you have alkaline hydrolysis and you have your acid hydrolysis, but soap is alkaline hydrolysis. All right. Okay. So last one. I think this is the last part of this question. Let me look. Oh no. Oh, all right. Good. I like the last question. Come back here to no class. After fermentation, the product is usually filtered and distilled. Suggest why distillation is necessary and draw a simple label diagram of the apparatus which can be used for the distilling the fermented product in the school's laboratory.
Sir, after fermentation, the product is usually ethanol and water. And to get a concentrated sample, fractional distillation is required to obtain.
All right. Hold on.
Ethanol.
Hold on. Don't forget what I said earlier, that the regular fermentation will only give you a certain percentage of alcohol.
I was getting to that, sir.
You should tell me that first.
Okay.
Yeah.
Okay, sir.
That's the first thing you should tell me. You get it?
No. Yes, sir. The fractional distillation will give you a concentrated or a higher percentage.
The distillation, yes. Now for the percentage when the yeast becomes denatured, it varies, but it is anywhere from, some people say 12, some would say 14, some would say 15, some would say 16, somewhere there. They will tell you the one that they're looking at. But if they ask to explain, if you give them 14, you can't go wrong either. Clear? Clear?
Yes, sir.
All right, so we're good there. This one now, let me see how you think about this one. In some countries, the breathalyzer test is used to determine the level of alcohol in the breath of suspected drunk drivers. Identify the main reagent used in the breathalyzer test, hence state the type of reaction that occurs during the test. Talk to me.
There is a potassium dichromate.
Yes, sir. Potassium dichromate, sir, and oxidation and reduction, sir.
All right, hold on there. Redox.
Just a sec.
Yeah, redox. I'm gonna come back here, sir.
Somebody's asking to explain that fermentation thing first.
Which part of the fermentation part you want me to explain?
I guess it's the equation with the swelling. Swellian, sorry. Could you explain to sir what you don't understand? Swellian Jones. Okay, I'm not getting a response.
All right, let me just run back through something. I hope it will help. Fermentation we're talking about, right? And again, sorry, let me just clear this. We're saying that in the fermentation process, you need to have your flask, and your flask must be closed. So you're gonna put the thing there, the delivery tube, and you close it off, seal it off, okay? This is a delivery tube that will come over into a test tube or a boiling tube that contains calcium hydroxide, which is your lime.
I think she wants to know why you do the distillation.
Oh, the distillate. Okay, all right. So we're saying then, because the yeast is here, Y-E-S-T, yeast is there, right? The enzyme zymase in the yeast, when you produce a certain level of alcohol, it is that percentage is too high. It's toxic for the yeast or for the enzyme. So you can't produce any more alcohol. You can't produce a higher percentage. So to get a higher percentage, fractional distillation is what you use to get a higher percentage of alcohol. All right. Again, I would have to go into boiling point curve and all that to show you. I could come from any side to show you that process, that distillation process. Okay. But we're not going into that right now. We just want to, I'm just saying to you that once you get a higher, once you get like 14% or so, that percentage is toxic for the yeast or the enzyme. So it becomes denatured. Once the enzyme is denatured, it cannot produce any more or a higher percentage of alcohol. So now, to get a higher percentage of alcohol, you must carry out fractional distillation. Tell me if you're okay with that. You okay with that, miss? If you can't talk, type
She
it.
says, okay.
All right. And you must now show the apparatus. So the fractional distillation, the fractionating column is what you would draw. Okay? So you draw your fractionating column, you draw the flask, you draw the condenser, you draw the collecting, whatever is collecting the alcohol. Okay? All right? Tell me if she's fine. Miss.
Yes, sir.
All right. Thank you. Moving back now to where we were. Okay, we were down here. I think this is the last question for this part. In some countries, the breathalyzer test is used to determine the level of alcohol in the breath. Oh, you told me already. You said identify the main reagent. All right. So what is the main reagent? The breathalyzer test.
The potassium dichromate.
All right. So it is something to do with dichromate. I think the main, so it's either potassium or sodium, some dichromate. No, you must use. Huh?
Potassium dichromate.
Yeah. Are you hearing me? Good. So the dichromate, fine. What color is the dichromate?
Sir, orange.
Orange.
Orange. All right, listen again. Listen to my question, you know, people. It's orange. All right, so dichromate is orange. Why is the dichromate orange? Why is the dichromate orange? Come on, people. Why is manganate purple?
So CSEC go ask us questions like this.
Hello, no. Hey, you're not easy. You're not easy, you know. Tell me why the thing is orange, huh? What you see the guys. Why is it orange?
Oh, sir, the presence of the concept. I don't even know. I'm just going to go off a limb and say the presence of the CR, the chromate ion, and the oxygen in it. So the
all right. Look at this. Look at this. K2Cr2O7. Right? This is the potassium dichromate. You agree? You agree?
Yes, sir.
If you if the redox reactions and you work out this, don't you get this to be +6? So the Cr, so the ion, the dichromate ion is Cr2O72 minus. So this is still +6. So the dichromate ion is orange because the charge on the Cr is +6. What is the color of Cr3 plus?
Green.
Green. Green. Why is it green? The presence of the 3+ oxidation state. Yes.
Yes, sir.
Yes. K MnO4. Why is this purple? MnO4 minus. Why is that purple? The presence of what?
Oxidation or oxygen.
The presence of the Mn, it carries
Or
a
the manganate.
+7.
Carries a
Yes, the
+7.
Mn carries a +7 charge. Now, when it is reduced, I go from +7 to 2+. All right, tell me if I'm wrong on people, because I don't want to tell no foolishness. You go to +2, not true. So it's reduction.
Yes,
so what they mean say that most people make most times, they say MnO4 minus and go to Mn2+, and they say it is oxidized because you go from -1 to +2. But no, you're looking at what is the charge on Mn. Am I clear so far?
Yes, sir.
All right. So this is reduction because Mn going from +7 to +2. This is purple because the Mn carries a +7 charge. This is orange because the Cr carries a +6 charge. Okay, good. Now you understand that now. Let's go back to the question. So you give me the reagent, right? The next part is what?
Reduced. It is reduced. So the reaction that happens is a redox. So
redox.
the
All right.
ion, the dichromate ion is reduced to the green color, which would indicate that alcohol is present in the breath.
All right. So the color is linked to certain numbers, right?
Yes,
and the
sir, to certain
more
numbers.
alcohol you have, then of course the deeper the color should be, which is suggesting you have more reduction taking place. Not true?
Yes, sir.
So reduction of the Mn of the Cr plus 6 Cr plus 3. All right. What is causing the Cr to be reduced?
Yes, sir, the alcohol.
The what?
Sir, the breath, sir. I guess it's
alcohol in the breath.
Or the alcohol in the breath.
Yeah, man, the alcohol in the breath. And now look here. When I see people like you're driving and they were drinking, and then see the police and them start eat ice mint and something, laugh at them because that will not affect the amount of alcohol in your blood. You're masking the scent from your mouth, but it will not affect the amount in your blood. The amount in your blood is what will come out of your lungs and go into the breathalyzer. Is that clear? So that will not affect anything at all.
Yes, sir.
All right. So look now. The alcohol is, what could you say the alcohol is acting as?
Oxidizing agent.
No, look here.
A reducing agent.
Yes, it's a reducing agent. Because remember now, the dichromate was reduced from +6 to 3+, not true?
Yes,
so
sir.
something caused it to be reduced. Now, what caused it to be reduced? The agent. So the agent is a substance that causes something to happen to cause the reduction. So a reducing agent is a substance that causes another substance to be reduced while itself is
oxidized.
Oxidized. Now, what will the alcohol be oxidized to?
Ethanolic acid.
Yes. So if you have both oxidation and reduction taking place, right? What is the type of reaction here? Redox reaction. Tell me if you're clear with this so far.
Very clear, sir.
Very clear. All right, good. Any question before I move on? Because we're done with this now. We're going on to 18 now. Any questions? No? All right. 18 then. 18. Number 3. All right. Doc, what do you think?
I'll just tell you the time and you tell me. Almost 4:45.
Wait, sir, it's a question. That means the reaction is the two of them. So just for redox, it's not only one.
Mr. Burrell? Okay, I'm not sure if we lost him for a bit. Mr. Burrell?
Hello?
Yes, we weren't hearing you for a bit.
Oh,
I was telling you that the time is 4:45. So
yeah, man. And I was just asking the question, you know, what do you think? What we have to stop now. Because yeah. But
Yeah,
ladies and gentlemen, let me.
If there are any lingering doubts or questions that you want to ask sir now, please do so.
Yes.
Okay, there's a raised hand from Deandra. Could you go ahead?
Yeah. Go ahead.
I was asking if the reaction would be the two of them, the redox and the oxidation.
No. When you have oxidation and reduction taking place at the same time, we call that redox reaction.
Okay, yeah, that's what I mean. Okay, thanks.
Yes. So that's a redox reaction, similar to what they call an acid-base reaction. You have acid-base, which is called neutralization reaction. Yeah, you have redox reaction. Yes. That's it. What else?
All right. Anybody else? Oh, somebody wants your PowerPoint. Anyway.
Miss, I'll send it to you, and you can send it to them.
Right. Okay.
I'll just put it in a PDF form. Okay.
Yes. Great.
Excuse me.
Yes, go ahead.
I know this is a ministry thing, but sir, do you offer private classes? If so, could I have your email address?
We can't have a private class on the ministries thing, Miss. Miss, type my email address. Let me type it. Let me type it in the chat.
Type in your yes. So if you want to contact sir privately.
Yeah, let me type it in the chat. Number of broadcast meeting over the internet.
In the chat. I have to get a commission from that, you know, sir.
Yeah. Miss, I don't normally advertise extra classes, you know. I'm sure I have some pros here that I teach. If you can ask them, I don't advertise extra classes.
Miss, are you going to send the video via
okay, so
email?
this recording will be posted and we'll send the link out as well. All right. So
along with the PowerPoint, right, Miss?
Well, when sir provides it, then we will send it out.
Yeah, man, I will give it to you.
All right, so any other questions, anything else to clear up? Is there anything that sir mentioned that you just didn't get before you leave?
All right, I'm gonna send it up. No, don't broadcast my thing, all right?
Oh, sorry.
Okay. All right, all that look.
Okay, the type of reaction was redox. Yes, some of those.
Yeah, redox.
All right. Final call. Any questions? Any lingering doubts? Any clarifications needed? All right, so go ahead and help me thank Mr. Burrell for doing an excellent, superb job this afternoon. He taught so well that he couldn't finish the number of questions that he came with. All right, so continue to please tell him how excellent he is.
you guys made it very easy for me, very easy. Along with Doc, of course. Doc, you have a very calming presence.
I hear you.
Yeah.
All right.
So thank you very much, everyone. Take care, and we will talk.
Thank you, sir. All right.
Yeah, man. Thanks a lot.